the sun unleashed a chilling spectacle. A colossal gash tore across its fiery surface, spewing a torrent of plasma straight toward Earth. At that very instant, the enigmatic interstellar comet 3I Atlas vanished from every telescope's gaze. Simultaneously, Mother Earth shuddered with a powerful earthquake. The mystery gripping everyone's thoughts is what just happened. Was Comet 3I Atlas obliterated or transformed into something new, and if it reappears, what strange form might it take? As this cosmic enigma fades into the shadows, another celestial marvel steals the stage. Comet Lemon, an ancient icy wanderer predating civilization itself, blazes across our skies. Here's why the next 2 weeks will be absolutely pivotal. Meanwhile, in China, physicists have pulled off a feat straight out of a sci-fi thriller, an unbreakable, unhackable communication network that exposes every secret. Don't blink, because before we wrap up, we'll unveil the must-know cosmic dates you can't afford to miss, including one flying under the radar that everyone should be buzzing about. If these enigmas have your pulse racing like they do mine, don't just sit there, take charge, smash that like button, hit subscribe, and stay glued as these mind-blowing stories unfold in real time. Leave a comment below with your location, the local time, and your honest take. Are we being fed the full truth about these earth-shattering discoveries? Want to fuel this community's growth? Share this video on X, Facebook, Reddit, or your group chats. Every share, comment, and click powers our pursuit. You're the heartbeat behind our relentless chase for these stories. We deeply appreciate your solidarity in this quest for answers. Part 1. The Vanishing Act. The sun unleashed a spine-chilling spectacle in October 2025, sounding a cosmic alarm that went unnoticed by most. Scientists vigilantly observing our star were gripped by mounting dread as a colossal transquatorial coronal hole tore violently across the solar surface. A jagged tear in the sun's magnetic field gaped like a cosmic wound, hemorrhaging invisible energy into the void of space. This was no ordinary solar event, no mere spark for dazzling auroras or minor satellite glitches. The chasm was monstrous, stretching across both the northern and southern hemispheres of the sun in a single awe-inspiring breach. A rare and ominous cosmic event unfolded, its full consequences still shrouded in mystery. A ferocious solar wind unleashed through a gaping tear in the sun's magnetic shield surged at a staggering 700 km/s. Picture a hurricane where every air particle roars at nearly 1.5 million mph. This relentless stream of charged particles, protons and electrons ripped from their atoms, hurtled toward Earth like a celestial fire hose aimed with unnerving precision at our planet's magnetic field. The alignment was flawless, almost eerily so. The solar wind's magnetic polarity aligned perfectly with Earth's field, locking into the exact configuration for maximum coupling, a fierce surge of energy from the sun's cosmic breath flooding our planet's magnetosphere. Geophysicists raced to forecast the fallout, while urgent warnings flashed to power grid operators. Satellite controllers braced for potential chaos, readying for malfunctions. Aurora chasers clutching their cameras raced north, eager for a solar onslaught that would ignite the sky with indescribable hues. Yet at that precise moment, something else erupted. A phenomenon that transformed this solar flare-up from a mere space weather event into a profound cosmic enigma. Comet 3I Atlas, only the second confirmed interstellar wanderer ever spotted in our solar system, vanished behind the sun's blazing veil. One moment it gleamed faintly, a ghostly streak of light, tracing an orbit born in a distant star system, bearing ice and rock forged in alien clouds around a sun forever beyond our sight. In a fleeting instant, it vanished into the sun's blinding glare, engulfed by the star's ferocious brilliance, invisible to every telescope on Earth and beyond. The timing was uncanny, impossible to dismiss. Earth's magnetic field reeled under the onslaught of the swiftest solar wind in months, while at the same moment, our sole interstellar messenger went dark, obscured by the very source of that cosmic assault. Scientists, meticulous by nature and trained to steer clear of hasty conclusions, repeatedly caution that correlation does not imply causation. They chose their words with precision when reporters probed whether these events might be linked. Then the ground began to quake. A series of magnitude 7 earthquakes rocked disparate regions of Earth mere hours after the solar winds slammed into our planet. Seismometers captured the ferocious tremors, a violent unleashing of tectonic energy that had been simmering for years, perhaps decades, in the strained rock beneath our feet. Statistically, such tremors were not entirely unforeseen. On average, Earth trembles with about 15 magnitude 7 earthquakes each year. Yet when multiple quakes strike in tight temporal sync, with a colossal solar eruption and the mysterious vanishing of an interstellar comet, it ignites a primal spark in our human pattern recognition system. That ancient corner of our minds relentlessly hunting for connections, yearning to extract meaning from mere coincidence. Could the sun's ferocious magnetic onslaught have sparked Earth's seismic upheaval? Mainstream science firmly rejects the idea, insisting that earthquake physics operates independently of solar forces. Tectonic plates, they argue, are indifferent to magnetic fields or solar winds, driven solely by the relentless grind of rock mechanics and pent-up strain energy. Yet dissenting voices from the edges of geophysics challenge this view, pointing to intriguing statistical quirks in earthquake timing during solar maxima. They propose bold theories invoking ionospheric coupling or minute shifts in Earth's rotation rate as potential mechanisms. These ideas haven't caught fire in peer-reviewed journals, but they spark fervent whispers in conference corridors and online forums, intriguing possibilities the mainstream hasn't fully debunked to universal satisfaction. Yet the comet holds the true enigma shrouded in cosmic mystery. 3 Atlas secured its place as the third confirmed interstellar wanderer to grace our solar system. The first 1I Oumuamua in 2017 was a peculiar elongated enigma that somersaulted through the inner solar system, displaying mysterious acceleration that defied the usual explanations of comet outgassing. The second 2I Borisov in 2019 felt more familiar, a comforting ball of ice and dust, behaving like the predictable comets we know, adhering to the reliable laws of physics. In 2025, the enigmatic 3I Atlas was spotted hurtling toward the Sun on a hyperbolic orbit, its velocity too ferocious to be tethered by our star's gravitational pull. Undoubtedly a fleeting visitor merely passing through on its cosmic journey back to the vastness of interstellar space. Such objects are extraordinarily valuable to scientific discovery. They're the sole fragments we possess from alien stellar realms, our only tangible link, until we master the technology to dispatch probes to distant stars and retrieve physical samples a feat far beyond our lifetimes. Each photon of light we capture from an interstellar comet pulses with secrets, clues about cosmic chemistry. The makeup of protoplanetary disks encircling foreign suns and whether the forces that forged our solar system are a universal blueprint or a singular anomaly. When the enigmatic Comet 3I Atlas vanished behind the sun's blazing veil, our ability to track its data was abruptly severed, at least for now. The question gripping astronomers is no longer just about solar flares, cosmic winds, or earthly quakes. It's far simpler and infinitely more unsettling. When Comet 3I Atlas re-emerges from the sun's shadow, if it emerges at all, will we even recognize what returns? Did our star consume this interstellar wanderer? Could the sun's ferocious heat, relentless radiation, and chaotic magnetic storms have reshaped it, shattered it, or vaporized it completely. The truth is imminent, and it could unravel everything we believe we understand about these cosmic visitors. Wanderers Part 2: The Traveler We Lost. The saga of Comet 3I Atlas unfolds like most cosmic discoveries with relentless patience. Night after night, automated telescopes sweep the heavens tirelessly, hunting for any speck that dares to drift against the steadfast backdrop of stars. The Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, wields 4 robotic telescopes strategically scattered across the globe. Their primary mission: to detect asteroids on a collision course with Earth. Yet these vigilant sentinels draw no lines of prejudice. They capture all that moves in the vast celestial sea. Anything that moves, including comets. And in the early months of 2025, they captured something extraordinary. The object appeared first as a faint streak in images from the Hawaiian stations. Follow-up observations from other facilities confirmed it was moving, and moving fast. Trajectory calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, indicating this object wasn't bound to the sun. It had come from somewhere else, and after its close approach to our star, it would continue on its path, departing back into the vast cosmic ocean between stars. The orbital energy didn't match anything native to our solar system. This was interstellar. The astronomy community mobilized swiftly. Telescope time, typically scarce and scheduled months in advance, was suddenly made available. Spectroscopy. The analysis of light reflected or emitted by the comet became the top priority. What was this thing made of? Did it carry the familiar mix of water, ice, carbon dioxide, ice, and organic molecules that define comets formed within our solar system? Or would its composition reveal an alien chemistry with elemental ratios hinting at formation conditions around a different kind of star? Early data suggested. A baffling mystery unfolded. The radiance of Comet 3I Atlas defied astronomers' predictions. Typically, comets blaze brighter as they near the sun, tracing a predictable arc, driven by the escalating sublimation of ice. As solar heat surges, water ice begins to sublime, transforming directly from solid to gas when sunlight warms the surface to roughly 200 degrees Kelvin. Other volatiles, such as carbon monoxide and carbon dioxide, transform into gas at even lower temperatures, sparking activity at far greater distances from the sun. The brightness curve of Comet 3 Atlas revealed intriguing pauses with periods of flattening where its glow didn't intensify, as models forecasted only to be followed by abrupt surges in luminosity, hinting at explosive bursts of dust or gas. The coma, that hazy veil of gas and dust enshrouding the comet's nucleus, glowed eerily faint in certain observations. The dust output was surprisingly sparse for a comet of its stature. Some scientists theorized that the nucleus could possess an exceptionally high density, dominated by rock rather than ice, accounting for its subdued activity. Some argued the contrary, proposing that the comet's nucleus was remarkably porous, resembling a loosely bound rubble pile barely held together by feeble gravity. This fragile structure triggered the ice to sublimate in erratic explosive bursts rather than a steady release. Then there were the mysterious non-gravitational forces at play. Comets defy the neat, predictable Keplerian orbits dictated solely by the sun's gravitational pull. As ice vaporizes from their nucleus, it unleashes powerful jets of gas functioning like miniature rocket thrusters that nudge the comet off its expected trajectory. These subtle yet detectable non-gravitational accelerations inject a thrilling uncertainty into forecasting a comet's precise position at any moment. For Comet 3I Atlas, these disturbances proved exceptionally challenging to predict. Its orbital calculations required constant refinement, with error margins shifting unpredictably, leaving astronomers grappling with growing uncertainty about the exact timing and location of the comet's reappearance from behind the sun's glare. Some observations even suggested potential fragmentation before it vanished entirely. Comet nuclei, delicate and loosely knit amalgamations of ice and rock, are prone to shattering under the strain of thermal stress or tidal forces. When a comet splinters, it frequently spawns a trail of smaller fragments, tracing near-identical orbits, occasionally appearing as multiple glowing knots within the coma. Observations of Comet 3I Atlas revealed tantalizing hints of asymmetry and elongation, subtle signs that its nucleus might have been unraveling. If the comet was indeed fracturing before it vanished from sight, the mystery surrounding its disappearance grows even more urgent. What might burst forth from the sun's blinding glare could be more than a single entity, perhaps a cascade of debris, or possibly nothing at all if the fragments have crumbled too small to be seen. Comparisons to past interstellar travelers were unavoidable. Take Oumuamua, the first confirmed interstellar visitor, which intriguingly was never definitively identified as a comet. It displayed no shimmering coma, no trailing dust tail, nothing to unmistakably mark it as an icy wanderer. Yet it surged away from the sun with an acceleration that defied the pull of gravity alone. The most plausible cause, comet outgassing, but not from ordinary water, something far more exotic, like carbon monoxide or molecular nitrogen. These volatile substances would sublimate silently, leaving no visible dust in their wake. The allure of exotic theories, from light sails to alien probes, ignited the public's imagination, yet garnered scant backing from scientists who prioritize hard evidence over conjecture. Meanwhile, Comet Ice Brusso mirrored the traits of a classic comet, flaunting a distinct coma and tail, with brightness fluctuations aligning closely with established comet models. Its spectrum unveiled water vapor and carbon monoxide, a chemical makeup mirroring comets in our solar system. This discovery felt oddly comforting, hinting that planetary formation around distant stars obeys similar laws, crafting comparable cosmic bodies. Yet Boris betrayed signs of fracturing as it neared perihelion, its closest dance with the sun. Stunning images revealed a fragment splintering off from the core of the comet's nucleus, a stark reminder that these cosmic wanderers often crumble during their perilous journey through the inner solar system. Now, Comet 3I Atlas was tracing a similar doomed trajectory, plunging toward the sun, and at the most critical moment, it slipped from every telescope's view. The geometry of solar conjunction, when an object slips behind the sun's blazing veil from Earth's perspective, carves out a maddening observation gap that can stretch for days or even weeks, dictated by the object's path and radiance. For a dim comet, already flickering with eerie, unpredictable behavior, this gap transforms into a cosmic black box, a mysterious void where anything might unfold, leaving us utterly blind to its secrets. The comet might be crumbling into oblivion. It could be blazing with breathtaking brilliance. Or perhaps it remains whole, shrouded too closely within the sun's blinding glare to be seen. We won't know until it reappears, if it reappears at all. Scientists scrambled to model its fate, piecing together predictions based on guesses about its nucleus size and makeup. If the comet's core is large and predominantly rocky, thermal simulations suggest it could endure shedding only a fraction of its mass. But if it's a smaller, icy body, the searing heat near perihelion might reduce it to nothing more than a fading wisp of gas and dust. The uncertainty surrounding its nucleus size is staggering, spanning from a mere few hundred meters to several kilometers, a discrepancy of tenfold or greater. This vast unknown ripples through every predictive model, transforming calculated forecasts into little more than educated guesses. Astronomers dubbed it the invisible interstellar traveler, a mysterious visitor from another star system, concealed behind the sun's relentless glow, beyond the reach of every telescope humanity has crafted. It's either defying the odds or disintegrating, and we're left powerless, waiting in suspense to see what, if anything, will emerge when the cosmic alignment finally permits a glimpse. The anticipation feels like an eternity squeezed into mere days. Part 3. When solar wind collides with alien ice. The sun is no gentle giant. We cherish it as the radiant, life-sustaining star that bathes Earth in warmth and light, nurturing our world. Yet peel back its serene facade and the sun reveals a savage nature, a seething, roiling sphere of plasma where temperatures soar to millions of degrees and magnetic fields coil like tightly wound springs brimming with volatile energy. When those springs unleash, the consequences can be catastrophic for anything in their path. In October 2025, a coronal hole tore open on the sun's surface, sending a shiver through the solar physics community. These enigmatic coronal holes are regions where the sun's magnetic field unfurls into space, no longer tethered to its fiery surface. These open field lines become cosmic superhighways, channeling solar wind streams of charged plasma racing into the solar system at breakneck speeds. While typical solar wind cruises at about 400 km/s, the torrent erupting from this coronal hole roared at a blistering 700 km/s, nearly double the speed. This high-velocity surge carried a ferocious payload of momentum and energy, primed for disruption. When this relentless solar wind slams into a comet unprotected by Earth's magnetic shield, the encounter ignites a fierce and intricate cosmic dance. They lack a magnetosphere to shield them from charged particles, leaving their coma vulnerable to the relentless solar wind. This torrent of energy crashes directly into the comet's halo of gas and dust, where bizarre physics takes hold. Solar ultraviolet radiation ionizes the coma's gas, transforming it into a vibrant swarm of electrically charged molecules. These ions, now sensitive to magnetic forces, interact with the solar wind's embedded magnetic field lines, which wrap around the comet like a cosmic cape. The result is a mesmerizing magnetotail, a dynamic structure born from the dance between the solar wind's magnetic field and the comet's ionized gas. This radiant tail stretches millions of kilometers downstream, trailing away from the sun, shimmering faintly with the glow of ionized carbon monoxide and other vibrant molecules. Far from a static feature, the tail dances dynamically, rippling and fluttering under the turbulent forces of the solar wind. At times, dramatic disconnection events unfold where the tail snaps off completely, only for a new one to begin its celestial rebirth. These cosmic interactions are observable from Earth, with specialized instruments offering tantalizing clues about the solar wind's behavior and the comet's gas production rate. But what happens when a comet already strained by the scorching heat near perihelion collides with an exceptionally fierce solar wind? History unveils some awe-inspiring and terrifying spectacles. In 2012, astronomers discovered Cometan, a celestial wanderer poised to blaze with breathtaking brilliance. Yet in 2013, as it swept perilously close to the sun, its anticipated glory unraveled. Solar observing spacecraft captured its dramatic journey entering the perihelion region as a radiant beacon, only to emerge as a fleeting, dispersing cloud of dust. Its nucleus, overwhelmed by the sun's ferocity, shattered entirely, leaving no trace of its former self. Defying all odds, Comet Lovejoy, a daring sun grazer, skimmed a mere 140,000 kilometers from the solar surface in 2011. Despite dire predictions of its destruction under crushing thermal and tidal forces, it emerged triumphant. Stunning images revealed its tail stretching millions of kilometers post-perihelion, a radiant stream fueled by torrents of gas erupting from its superheated nucleus, a testament to its astonishing resilience. The astonishing survival of Comet Lovejoy defied all expectations, leaving scientists scrambling to unravel the mystery. A unique blend of its nuclear size composition and structural resilience enabled it to withstand scorching temperatures that should have obliterated it entirely. Meanwhile, 32 Atlas ventured into a perilous zone where the sun's influence reigns supreme, navigating this treacherous region during an unusually ferocious solar windstorm. The critical question loomed: would the combined onslaught of thermal stress, radiative heating, solar wind pressure, and potential prior fragmentation prove too much, tearing the comet apart? Some researchers dared to explore bolder theories. A fringe group of plasma physicists championed the electric comet model, proposing that comets accumulate electrical charges as they interact with the solar wind. They argue that these electrical forces, not merely thermal sublimation, fuel the comet's dynamic behavior. Mainstream astronomers remain skeptical, asserting that conventional physics sufficiently explains observed phenomena without invoking exotic electrical effects. Yet advocates of the electric model point to striking evidence such as abrupt disconnection events in comet tails and sudden dramatic brightness shifts as compelling signs that electrical processes are at play. The hypothesis ventures deeper into uncharted realms, proposing that intense solar wind events could trigger charge separations within a comet's coma, potentially sparking explosive disruptions or abrupt trajectory shifts far beyond what mere outgassing could explain. Yet the evidence supporting these bold claims remains fiercely debated. The theoretical framework remains unfinished, yet its ideas ripple through discussions driven by their bold attempt to account for observations that defy conventional models. When Comet 3I Atlas mysteriously vanished amid a massive solar wind event, advocates of electric comet models seized the moment, viewing it as a striking validation of their theories. Mainstream astronomers witnessed a cascade of events, dismissed as a tragic yet purely coincidental convergence. The mystery deepens with our ignorance of Comet 3I Atlas's true nature. Sparse spectroscopic observations before its vanishing act offered only fragmented clues, leaving its composition a puzzle. It might be dominated by water ice akin to typical solar system comets, or perhaps carbon monoxide ice which vaporizes at far lower temperatures, fueling activity even at vast distances from the sun. Alternatively, it could be laden with silicates and sparse in volatiles, resembling an asteroid more than a comet. A typical comet's core is a complex blend, each element reacting uniquely to the sun's scorching heat and relentless solar wind. If the nucleus is extraordinarily porous, resembling airy aerogel, with a density scarcely greater than the surrounding coma's gas, thermal waves would burrow deep, warming, hidden ice reserves. This could trigger a catastrophic collapse as the entire structure disintegrates in a breathtaking cascade of sublimation. If the nucleus is shrouded in an insulating dust mantle across most of its surface, gas production would surge from a handful of active regions, unleashing powerful jets that might whip the nucleus into a frenzied spin or twist its rotation in erratic, unpredictable ways. If the nucleus is a contact binary, two lobes barely clinging together under feeble gravity, tidal forces and thermal stress could wrench it apart. In this cosmic drama, the sun emerges as a formidable gatekeeper, a destructive force that ruthlessly challenges every object daring to traverse the inner solar system. Interstellar comets born in alien environments with potentially unique structural properties compared to our solar system's comets might prove especially vulnerable, or perhaps more resilient, forged in conditions that rendered them tougher. The truth remains elusive until we witness what survives this celestial gauntlet. The parallel to Comet Shoemaker-Levy 9 offers a compelling lesson. In 1992, a cosmic drama unfolded as Comet 3I Atlas ventured too close to Jupiter, only to be ripped asunder by the planet's relentless tidal forces. Shattered into over 20 fragments, these remnants later plummeted into Jupiter in a breathtaking cascade of collisions. The tidal disruption occurred because Jupiter's immense gravity gradient stretching across the comet's diameter overpowered its own feeble self-gravity, tearing it apart with ruthless precision. The Sun's tidal grip, though feeble at the distance where Comet 3I Atlas swept by, could still prove deadly. A comet already battered by thermal stress or earlier fragmentation might crumble under forces that a robust nucleus would effortlessly shrug off. Has the Sun just unveiled a chilling secret about these interstellar wanderers? The truth hinges on what we discover when the comet reemerges from its conjunction with the Sun. Should the enigmatic 3I Atlas reemerge unscathed, tracing its hyperbolic path with steady streams of gas and dust, the solar wind eruption fades into a mere side note. A fleeting coincidence that ignited curiosity but carried no deeper meaning. Yet if the comet has shattered or vanished entirely, we're confronted with unsettling mysteries, our interstellar wanderers inherently more delicate than our theories suggest. Could their origins or composition render them susceptible to solar onslaughts in ways we never foresaw? In the gripping fourth chapter, the cosmic vigil ignites. Astronomers are feverishly circling dates on their calendars, poring over ephemerides and meticulously crafting observation plans for the pivotal moment when Comet 3I Atlas might reemerge into view. The timeline hinges on a web of variables, the comet's elusive trajectory muddied by unpredictable non-gravitational forces, its brightness, which may have undergone a dramatic transformation, and the observing geometry dictating how far the comet must stray from the Sun's glare before telescopes can pierce the celestial backdrop to spot it. Current projections tantalize with possibilities suggesting the comet is expected to reappear from its solar conjunction in late October or early November 2025, achieving enough angular separation from the Sun, as viewed from Earth, to become visible with advanced equipment. Early efforts to spot it will likely rely on space-based observatories, which can more effectively shield the Sun's glare compared to ground-based telescopes. The Solar and Heliospheric Observatory is equipped with advanced coronagraphs that ingeniously simulate eclipses, unveiling the Sun's secretive surroundings where comets often lurk unseen. Meanwhile, Mysterio, the Solar Terrestrial Relations Observatory, deploys 2 spacecraft in solar orbit, capturing unique perspectives that could spot these elusive comets far sooner than any Earth-based telescope. The Parker Solar Probe, humanity's boldest venture to touch the Sun, traces a daring orbit that sweeps it closer to our star than Mercury itself, plunging through realms where solar winds howl at ferocious speeds and temperatures soar to unimaginable extremes. Should its path align near 3A Atlas during the comet's conjunction phase, the probe's cutting-edge instruments could seize unprecedented data unveiling secrets of the comet in conditions beyond the reach of any Earth-bound telescope. The Parker Solar Probe's mission is laser-focused on unraveling the mysteries of the solar corona and solar wind not chasing comets. For it to capture data on a comet, that comet would need to serendipitously drift into the probe's narrow field of view at precisely the right moment, an unlikely cosmic alignment. So far, mission scientists haven't reported any such fortunate encounters, hinting that either the geometry was off or the comet was simply too dim to stand out against the dazzling solar backdrop, leaving Parker's instruments without a trace to detect. What will the initial recovery images reveal? In the best-case scenario, the comet emerges as anticipated, possibly a tad dimmer from dust depletion, yet strikingly intact, flaunting a vibrant coma and a flowing tail that signal vigorous ice sublimation from its nucleus. Its spectral signature would gleam with recognizable traces of water vapor, cyanogen, and carbon monoxide molecular hallmarks that vividly affirm the comet's composition. The comet's tail, with its length and intricate structure, reveals vital clues about the rate of gas production and the influence of solar wind in the post-conjunction phase. Astronomers would meticulously measure its brightness, comparing it to pre-conjunction levels, to determine if the comet sheds substantial mass during its perilous closest approach to the Sun. In the most dire scenario, the comet vanishes entirely. The night sky, where the majestic 3A Atlas once blazed, remains hauntingly empty, hinting at its complete disintegration. The nucleus shattered into fragments too tiny to detect individually or evaporated completely, leaving behind only a faint dispersing cloud of gas too thin to stand out as a distinct entity. While this outcome would be a scientific letdown, it's not without precedent. Several comets have vanished after daringly close encounters with the Sun, their disappearance serving as a critical clue in unraveling the complex physics of comet fragmentation. Yet between total loss and survival, a spectrum of thrilling possibilities exists. The comet might re-emerge as a cluster of fragments, or as a dazzling string of condensations stretching along its orbit, revealing that the nucleus has split, but its pieces defiantly endure. Fragment streams, though, challenging to detect, due to each piece being dimmer than the original nucleus, offer critical insights into nuclear structure and the dynamics of disintegration. Should the 3 Atlas return as fragments, analysts would meticulously measure the separation distances and velocities to piece together the timing and mechanics of the breakup. Alternatively, dormancy remains a possibility. The comet might have depleted its near-surface volatiles during its close brush with the Sun, forming a darkened, hardened crust that halts further sublimation until intense solar heat fractures the crust or erosion unveils fresh, pristine ice. Dormant comets masquerade as asteroids, displaying no vibrant coma or glowing tail, just a stark, rocky surface glinting faintly under sunlight. Should 3 Atlas slip into dormancy, we'd lose the chance to probe its gaseous makeup, yet we'd uncover valuable clues about its surface dynamics and the creation of insulating mantles. The most captivating possibility lies in an abrupt, dazzling brightening that could steal the cosmic spotlight. Occasionally, comets shatter in dramatic fashion, unveiling pristine, volatile-rich material to the Sun's rays, triggering abrupt surges in gas production and dazzling brilliance. A splintering nucleus can spawn fresh, active zones, expanding the total surface area that sublimates. If 3 Atlas fragments erupt and ignite simultaneously, the comet that rises from the spectacle could outshine the one that vanished, captivating all who behold it. Although it exists in a fragmented state, it would probably dissipate rapidly as the tiny fragments exhaust their ice reserves. Spectral diagnostics will be essential. Pre-conjunction observations revealed the characteristic signs of water and possibly carbon monoxide, yet a comprehensive spectral inventory was never fully acquired. Post-conjunction spectroscopy could unveil a fascinating array of molecular species previously undetected, either due to the comet's limited production of these compounds, or because our observations missed the critical wavelengths. Vibrant oxygen emission lines would signal active water sublimation, while CN cyanogen signatures hint at intriguing carbon-nitrogen chemistry unfolding in the comet's coma. Additionally, the presence of sodium and iron lines occasionally glimpsed in comets could reveal the exposure of metallic-rich material from deep within the nucleus, offering a captivating glimpse into its hidden composition. Amateur astronomers are vital to the recovery mission. A global network of backyard telescopes delivers round-the-clock sky monitoring, surpassing the capabilities of professional observatories, constrained by limited observing windows and fixed schedules. Should the comet Atlas suddenly flare up or break into widely scattered fragments, these dedicated amateur stargazers could be the first to spot the change. Crowdsourced astronomy is gaining thrilling momentum as advanced digital cameras and powerful software empower passionate amateurs to deliver observations that rival the precision of professionals. A captivating cosmic mystery is unfolding live, inviting anyone with a telescope and clear skies to join the adventure and contribute to unraveling the universe's secrets. The comet might burst back into view at any instant, provided it endured its fiery trial. Or days could slip by, then weeks with no trace in the sky, until astronomers with heavy hearts accept that 3A Atlas has vanished. Shattered by the sun's relentless blaze, it journeyed so far, only to meet its end. The suspense is both tormenting and thrilling in equal measure. No probe was launched to meet this celestial wanderer. We're left with no means to actively hunt for it, save for aiming our telescopes at its predicted path and waiting in suspense. All we can do is gaze, speculate, and brace ourselves for whatever might emerge from the sun's blinding glare. A deeper question gnaws at the astronomical community if the nucleus has vanished. Do we still have 3 Atlas comets? Or are we left with mere debris, a scattered veil of dust and gas that once formed an interstellar comet, now no longer a distinct entity? Philosophically, it mirrors the ship of Theseus' paradox. If every piece of the original is gone, what remains? If a wooden ship has every plank beam and nail replaced over time, does it remain the same vessel? If a comet shatters into 1,000 fragments, each tracing nearly the identical orbit and bearing material from the original nucleus, do they together still form the comet, or has the comet vanished entirely? No formal definition exists to settle this enigma. It's a question of tradition and practicality, with researchers offering varied responses based on their viewpoints. Yet the question carries weight, because the 3A Atlas embodies something invaluable and unique, a rare glimpse into another star system. Losing it would mean far more than merely losing a celestial object. It's as if we've lost a fragile tether to the boundless cosmos, a delicate thread tying us to the broader galaxy, snapped before we could truly comprehend its significance. Part 5. When coincidence morphs into conspiracy. Why does this resonate beyond the esoteric pages of planetary science journals or the hushed discussions at astronomy conferences? Because we as humans are wired to hunt for patterns, evolved to uncover meaning in mere correlations, to perceive connections even where none may exist. This instinct drives us to question the eerie synchronicity of a colossal solar event and the sudden vanishing of an interstellar comet. A series of massive earthquakes has rocked our planet, setting off every instinctual alarm in our collective psyche, urgently signaling that something profound is unfolding. The prevailing scientific consensus on the link between solar activity and terrestrial earthquakes remains crystal clear and unequivocal. Earthquakes are propelled by the relentless dance of plate tectonics, where lithospheric plates glide atop the convecting mantle, driven by the gradual buildup of strain energy in the crust that ultimately overcomes the frictional forces keeping faults firmly locked. Solar activity lacks any credible mechanism to initiate this release. Magnetic fields have no impact on rock formations. Solar wind particles are unable to reach Earth's surface as they are blocked by the magnetosphere and atmosphere. Moreover, the thermal energy from solar radiation is insignificant when compared to the immense internal heat generated by Earth itself. Every examination of earthquake catalogs searching for connections to solar cycles or specific solar events has uncovered no evidence beyond mere coincidence. Yet intriguing correlations persistently emerge within the data, teasing with patterns that hover just below statistical significance, refusing to fully vanish. A cadre of bold researchers, operating on the fringes of mainstream science, relentlessly probes the mysteries of unconventional mechanisms. Might ionospheric turbulence sparked by solar activity alter the electrical characteristics of fault zones? Could minute shifts in Earth's rotation speed or magnetic field alignment driven by the solar wind's momentum subtly influence tectonic stress too faint to measure directly, yet potent enough to nudge a fault teetering on the brink of rupture? Is it possible that magneto-hydrodynamic coupling between the ionosphere and conductive crustal layers channels energy in ways we have yet to fully grasp? Understood. Here's your rewritten version with enhanced style and appeal, but preserving every detail and character. These ideas encounter immense skepticism because extraordinary claims demand extraordinary evidence, and the evidence remains at best circumstantial. Yet the human mind doesn't function by statistical significance thresholds. It operates through narrative, through stories that weave disparate events into coherent wholes. When the sun erupts, earthquakes rumble, and a comet disappears. All within a single news cycle, the narrative practically writes itself, even if the physics refuses to cooperate. The interstellar origin of the three Atlas adds yet another layer of mystery and speculation. These objects hail from beyond our solar system, from realms we can scarcely imagine, shaped by materials whose composition and isotopic ratios may diverge wildly from the norms of our solar neighborhood. They're literally alien in the most precise sense of the word. And humanity has always cast its hopes and fears onto the alien and the unknown. When Oumuamua displayed acceleration that couldn't be readily explained by standard comet outgassing speculation, surged about artificial origins, about alien probes on reconnaissance missions, about technologies that surpass our comprehension, the simplest explanation still pointed to natural processes. Yet the alien probe hypothesis seized the public imagination. It fulfilled narrative desires that sterile scientific papers on carbon monoxide sublimation could never reach. The disappearance of the three Atlas during a solar storm invites the same kind of speculation. Did the comet carry something, encode something that marked it as a target? Are we witnessing a kind of cosmic quarantine protocol, the sun acting as guardian obliterating potential threats from interstellar space before they can infiltrate the inner solar system? The scientific absurdity of such ideas does nothing to dull their psychological allure. We crave a universe brimming with mysteries deeper than orbital mechanics and spectroscopy. We yearn for hidden meanings woven into celestial alignments. We want comets to be more than mere dirty snowballs. We want them to be messengers, bearers of information, of life, of purpose. The panspermia hypothesis. The notion that life propagates through the cosmos aboard comets and asteroids offers a scientific sheen to these longings. If comets once ferried the organic precursors that gave rise to life on Earth during the heavy bombardment billions of years ago, then each one becomes a potential seed carrier. And interstellar comets especially take on a rarefied significance vessels that might carry the chemistry of distant biospheres orbiting other suns. The destruction of 3I Atlas, if that's truly what occurred, becomes the loss of a biological sample, a cosmic library burned before its contents could be read. Meanwhile, more exotic interpretations swirl through fringe communities. Proponents of the electric universe theory view the sun's encounter with the comet as proof of plasma dynamics that they insist mainstream science refuses to acknowledge. They point to the comet's unusual brightness fluctuations, the intensity of the solar wind, and the disconnection events recorded in other comet tales, arguing that such phenomena demand electrical, not gravitational or thermal explanations. Yet the mathematics behind their models seldom survives rigorous scrutiny. Their predictions often fail to align with observations, yet the intuitive allure of electricity as a universal force endures. The sheer visual drama of lightning and sparks grants electric universe ideas a resilience that outlives their scientific flaws. And inevitably, conspiracies arise, Are space agencies concealing data from the Parker Solar Probe's close encounters with the Sun? Did instruments capture images or spectra of 3I Atlas during the conjunction period that officials chose to withhold? What could possibly motivate such secrecy? Perhaps the comet displayed behavior that defied explanation, challenged core assumptions, or even sparked fear, prompting silence where transparency might have prevailed. People who grasped the implications might have been unsettled. Perhaps it fragmented in a way that defied natural processes or emitted signals or altered its trajectory as if under control. Such scenarios, of course, are exceedingly improbable, teetering on the edge of the impossible. But in minds predisposed to distrust official narratives, the absence of evidence becomes evidence of conspiracy. The psychological role of such theories is well documented. They offer a sense of control, or at least the illusion of it, amid randomness and chaos. They transform a universe of meaningless coincidences into one of hidden order and intent, even if that intent is dark or malevolent. It's easier, more comforting to believe in conspiracies than to accept that earthquakes strike at random, that comets disintegrate without reason, that we are fragile flickers of consciousness, adrift on a small world, racing through an indifferent cosmos. The tale of hidden knowledge and suppressed truth is far more emotionally gratifying than the slow, uncertain story of science, its patient investigations, its cautious steps toward provisional understanding. But here's the thing. Sometimes the universe really does align in ways that strain belief. Sometimes coincidences feel too precise, too intertwined to dismiss even when causation remains elusive. The October 2025 convergence of events, the solar storm, the comet's disappearance, the earthquakes may well be just that. An astonishing coincidence so improbable, it commands our attention even if in the end it signifies nothing at all. Or it might be the first glimmer of connections we've yet to comprehend, subtle couplings between geophysical systems and space weather operating beneath the limits of our current instruments. Science advances by probing anomalies, not by dismissing them. The researchers studying potential links between solar activity and earthquakes are pursuing legitimate, if admittedly speculative, science. They'll probably find nothing, but the search itself is valuable. When 3I Atlas reappears from behind the Sun, if it reappears at all, we may not even recognize it. The comet that went in might not be the same one that comes out. And when astronomers publish their analyses offering explanations rooted in physics, chemistry, and orbital mechanics, some will accept those findings and move on. Others will keep searching for hidden meanings, seeking links between the comet, the earthquakes, and the solar storm that go beyond mere material causation. Both reactions are profoundly human, each revealing our deep need to find meaning in a cosmos that presents more questions than answers. The Sun unleashed something terrifying, a comet vanished, and the Earth shook, and whatever truth lies beneath those events left us with equal parts wonder and unease. Part 6. The Comet We Can See. While 3I Atlas plays hide-and-seek behind the Sun, another comet is putting on a show you can truly witness if you know where to look and are willing to rise before dawn or stay up late after sunset. Comet C2025A6, discovered by the Mount Lemmon Observatory in Arizona, and thus nicknamed Lemon, is nearing its own close encounter with the Sun. It's brightening enough to be visible through binoculars or small telescopes, and under dark, clear skies away from light pollution, it might even be seen with the naked eye. The next 2 weeks mark the optimal viewing window. Lemmon's perihelion, its closest approach to the Sun, is set for mid-November 2025, but the geometry of its orbit means it will reach peak visibility from Earth just before perihelion, when it remains far enough from the Sun's glare to be observed comfortably. The comet is currently visible in the pre-dawn eastern sky, rising a few hours before the Sun. It glows with the soft, fuzzy light typical of an active comet, featuring a well-developed coma and possibly a short tail. Current magnitude forecasts place Lemon between magnitude 4 and 5, right at the edge of naked eye visibility. Under ideal conditions, the human eye can typically see objects down to magnitude 6. Magnitude 4 should be easily visible away from city lights, though spotting it without binoculars demands knowing exactly where to look. The comet is currently traveling through the constellation Cancer, moving eastward against the background stars. Finder charts available online clearly show its path relative to familiar star patterns, making it easier to track. Observing comets calls for patience and dark skies. Unlike planets, which appear as sharp points or disks, comets are diffuse. They spread their light over a larger area. This diffuse nature makes them far more vulnerable to light pollution and sky conditions than compact objects of similar overall brightness. A magnitude 4 comet can disappear entirely in bright suburban skies, even where magnitude 4 stars remain visible. Success means traveling away from urban lights to spots where the Milky Way stretches overhead, and the darkness allows your eyes to pick out faint, extended objects with low surface brightness. Binoculars are the perfect tool for comet watching. They offer enough magnification to focus the comet's light while maintaining a wide field of view, making it easier to locate and track the object. 7H50 binoculars, a popular size among amateur astronomers and nature enthusiasts alike, work especially well for this purpose. Mount them on a tripod if possible to eliminate handshake and allow for longer, steadier viewing sessions without fatigue. Through binoculars, the comet will appear as a small, fuzzy patch, distinctly non-stellar, sometimes tinged with a faint green hue caused by emission from diatomic carbon molecules in the coma. A telescope can reveal even more the structure of the coma, potential jets or fans of material erupting from active regions on the nucleus and the tail, if it has developed enough to be seen. But higher magnification comes at a cost. It narrows the field of view, making the comet harder to locate at first, and more difficult to keep centered as Earth's rotation slowly shifts the sky. For this reason, many seasoned comet observers prefer binoculars not just for practicality, but for aesthetic reasons. The wide field reveals the comet in context, set against star fields and the arc of the Milky Way, highlighting its role as a fleeting visitor drifting through a backdrop of more permanent celestial fixtures. Early observations of Lemon revealed something that has Comet. Scientists both nervous and excited, its brightness wasn't aligning perfectly with prediction models. Comets are famously difficult to forecast because their brightness depends on variables we can't directly measure, like the size of the nucleus, its composition, rotation, state, surface characteristics, and the ratio of dust to gas it releases. Models rely on assumptions drawn from statistical averages of other comets, but individual comets frequently defy those norms. Lemon has displayed periods of unexpectedly rapid brightening, followed by plateaus, where its brightness held steady even as it moved closer to the sun. These deviations could point to a number of underlying phenomena. Outburst activity, where fresh volatile material is suddenly exposed, can trigger a temporary surge in gas and dust production, leading to rapid brightening. Additionally, the rotation of the nucleus can bring different hemispheres into sunlight. If one side is more active than the other, this can result in periodic variations in brightness as the comet spins. Or more ominously, these deviations could signal the early stages of fragmentation, when the nucleus begins to break apart under thermal or tidal stress. Fragmentation is the hidden danger that shadows every comet prediction. A comet might appear perfectly healthy, brightening as expected, on its approach to perihelion, only to suddenly begin disintegrating. The process can unfold abruptly or stretch out over days or weeks, but once it starts, the outcome is rarely favorable for sky watchers. Sometimes a large fragment breaks away, forming a separate condensation visible near the main nucleus. Other times, the entire nucleus crumbles into a cloud of small fragments, each too faint to detect individually, but together producing a striking surge in overall brightness as their combined surface area accelerates sublimation. The physics of fragmentation involves a complex interplay of mechanical strength, thermal stress, and spin state. Comet nuclei are fragile, more akin to compacted snow than solid rock, held together mostly by their own weak gravity with a bit of added cohesion from internal ices and possibly sticky organic tars. As the sun heats one side of the nucleus, thermal expansion sets in, creating stress within the structure. If the nucleus is spinning, centrifugal forces introduce additional mechanical stress, and outgassing jets can generate torque that gradually spins the nucleus up to faster rotation rates. Eventually, the accumulated stress can exceed the material's strength, cracks begin to propagate, and the nucleus splits apart. In the case of lemon sublimation, science adds yet another layer of complexity. The comet appears to be driven by carbon monoxide or carbon dioxide sublimation, as much as if not more than water sublimation. These molecules are significantly more volatile than water, meaning they sublimate at lower temperatures and much farther from the sun. A carbon monoxide-driven comet can become active well beyond the snowline, where water ice remains frozen, generating a coma and even a tail while still in the outer solar system. As the comet draws closer to perihelion and temperatures climb, water sublimation eventually becomes the dominant driver, often triggering a shift in activity patterns and brightness behavior. The interactions between the tail and the solar wind offer yet another fascinating observational opportunity. Lemon's ion tail. If it develops, one will point directly away from the sun, blown outward by the solar wind like a windsock. Meanwhile, the dust tail traces a curved path composed of particles pushed by solar radiation pressure, but still carrying the orbital motion they had when released from the nucleus. These two tail types, ion and dust, often separate into distinct structures visible in photographs. The ion tail typically appears bluish, glowing from carbon monoxide ion emission, and is usually straight, sometimes featuring streamers and knots caused by magnetic field irregularities in the solar wind. The dust tail appears yellowish-white, glowing with reflected sunlight. It's broader and more diffuse than the ion tail, curving gently away from the nucleus. Comparing Lemon to 3I Atlas highlights fundamental differences between solar system native comets and interstellar visitors. Lemon formed roughly 4.6 billion years ago within the disk of gas and dust surrounding the young sun, most likely in the cold outer regions beyond Neptune, where temperatures were low enough for water and other volatiles to freeze into ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, that vast spherical reservoir of comets surrounding the solar system, at distances reaching up to 100,000 astronomical units. Then something, perhaps the gravitational influence of a passing star or a giant molecular cloud, disturbed Lemon's orbit, sending it hurtling back toward the sun on the very journey we are now witnessing. Its composition reflects the primordial chemistry of our solar system, the isotope ratios and molecular abundances typical of our local region of the galaxy some 4 billion years ago. 3I Atlas, by contrast, formed elsewhere around a different star under conditions that may have been either similar or radically different. The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, and the timing of planet formation, all these factors shape a comet's composition and structure. By comparing interstellar comets to those from our own solar system, we're essentially examining samples from different stellar nurseries, searching for commonalities that reveal universal processes and differences that spotlight local variations. Lemon serves as a real-time reminder of just how fragile comets truly are. Every comet is a gamble against disintegration. Most survive their perihelion passage, shedding some mass through sublimation before retreating back to the outer solar system or beyond, still intact. But some fragment, dramatically putting on spectacular shows as multiple nuclei and expanding dust clouds brighten and fade across the sky. A few vanish entirely, destroyed so completely that tracking them afterward becomes impossible. Watching Lemon during its peak visibility isn't just about appreciating a beautiful celestial sight. It's about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud, now running a gauntlet of solar heat and radiation that may or may not end in its destruction. The timing couldn't be more fortuitous. While 3i Atlas hides behind the sun, Lemon offers a worthy substitute, a different comet we can actually observe and study firsthand. If you've never seen a comet with your own eyes, if your experience has been limited to images on screens or diagrams in textbooks, now is your chance. Go outside before dawn, find a dark spot, let your eyes adjust for 10 to 15 minutes, and scan the eastern sky in Cancer. That fuzzy patch of light, if you spot it, holds ice formed before Earth existed, organic molecules older than life itself, and silicate dust that predates our planet. You're witnessing a messenger from the dawn of the solar system, and in just 2 weeks, it will fade from view. Its brief moment of visibility and its ultimate fate, whether survival or disintegration, remain unwritten. Watch the skies now while Atlas hides. Part 7. The Swan and the Context. Comets often seem to arrive in clusters, or at least that's how it appears to those tracking these icy visitors. The reality, however, is more prosaic. At any given moment, countless comets orbit the sun at varying distances, most too faint to detect without large telescopes. A handful are bright enough to catch the eye of amateur astronomers, and very rarely one becomes spectacular enough to be visible to the naked eye and capture public imagination. The clusters we perceive are largely the result of observational bias and the statistical nature of comet discoveries, yet they still create windows where comet watchers have multiple targets to track. The year 2025 is shaping up to be one of those exciting periods. Alongside Lemon and the vanishing 3i Atlas, another comet designated C2025R2 Swan has entered the catalog. Swan is named after the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce enormous hydrogen clouds, neutral hydrogen atoms created when water molecules break apart under the sun's ultraviolet radiation. These clouds are invisible to optical telescopes, but glow brightly at specific ultraviolet wavelengths, allowing Swan to detect them from vast distances, sometimes spotting comets months before they become visible to ground-based observers. C2025R2 Swan was discovered through its hydrogen corona, that immense invisible cloud enveloping the visible coma. Follow-up optical observations confirmed the discovery and enabled precise trajectory calculations. The comet is following an elongated elliptical orbit that will bring it to perihelion in early 2026, well after Lemon's close approach, but soon enough to keep comet observers engaged as they prepare their equipment and observation plans. Early brightness estimates for Swan suggest it might reach magnitude 6 or 7 at perihelion, making it primarily a binocular target, but likely not visible to the naked eye except under exceptional conditions. These predictions hinge on assumptions about the nucleus size and activity level, both of which remain uncertain. Some comets discovered by Swan have exceeded expectations, brightening dramatically as they near the sun. Others have disappointed, remaining faint and diffuse despite hopeful predictions. The only way to know for sure is to watch and wait. One intriguing possibility linked to new comets involves meteor showers. As a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high speeds, typically between 30 and 70 km/h, and vaporize in brilliant streaks we call meteors or shooting stars. Most meteor showers we enjoy annually, like the Perseids in August or the Geminids in December, happen because Earth passes through well-established dust trails left by comets that have made multiple perihelion passages, depositing dust over centuries or even millennia. New comets making their first journey through the inner solar system can produce unpredictable meteor activity. The dust along their orbits hasn't been evenly spread out by repeated passes and planetary perturbations. Fresh outbursts may create dense clumps of particles leading to sudden and unexpected meteor displays. If Earth happens to pass through one of these dense clumps, meteor rates could spike dramatically, potentially creating a meteor storm with hundreds or even thousands of visible meteors per hour. Such events are rare and notoriously difficult to predict because they depend on the exact spatial distribution of dust, which we cannot measure directly. Swan's orbit will be calculated with increasing precision in the coming months, allowing astronomers to assess whether any potential intersections with Earth's path through its dust streams might occur. Even the mere possibility, however low, of a meteor shower gets Comet and meteor enthusiasts buzzing with excitement. Witnessing a meteor storm is a bucket list experience, a celestial fireworks display that might grace the skies only once or twice per generation. These meteors appear to radiate from a point in the sky called the radiant, a visual effect, created by the converging perspective of parallel particle trajectories entering Earth's atmosphere. During a storm, the entire sky seems to rain meteors, streaks of light shooting in every direction, overwhelming the senses in a way that no photograph can truly capture. But for every comet that brightens and dazzles as hoped, several others fizzle out. The history of comet astronomy is filled with predictions that didn't pan out, objects once expected to become great comets that instead remained faint and unremarkable. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but barely reached naked-eye visibility, disappointing millions who had been promised a spectacular show. Comet Ison in 2013 was expected to survive perihelion and brighten dramatically, but instead disintegrated. These failures teach humility and remind us just how much we still don't understand about comet physics. The comparison between Swan and Lemon's brightness curves will ultimately yield valuable scientific insights. Observing two comets simultaneously under similar solar conditions offers a rare opportunity to directly compare activity levels and sublimation physics. Differences in brightness at comparable distances from the Sun reveal variations in nucleus size composition or surface properties, helping scientists unravel the complexities of comet behavior. If one comet is water-dominated and the other driven by carbon monoxide, their activity profiles will diverge in distinctive ways. If one fragments while the other remains intact, we gain crucial clues about the structural differences that govern a comet's fragility. Using Swan and Lemon as foils adds a layer of narrative tension. Many comets fail, so will 3 Atlas share that fate? Is there something about the current solar environment that makes comet survival more precarious than usual? The October 2025 coronal hole event might have been a singular anomaly, or it could herald a phase of heightened solar activity that imperils any comet venturing through the inner solar system. As the Sun's 11-year activity cycle nears its solar maximum sunspots and coronal mass ejections become more frequent, while solar wind speeds and magnetic field strengths intensify, amplifying the challenges for passing comets. Comets approaching perihelion during solar maximum endure far harsher conditions than those arriving during solar minimum. The history of comet fragmentation offers sobering lessons. Comet Shoemaker Levy 9's tidal disruption by Jupiter in 1992, culminating in its spectacular impacts in 1994, showed just how completely a comet can be torn apart by gravitational and tidal forces. Similarly, Comet 73P Schwarzmann-Wachmann 3 fragmented during its 1995 apparition, splitting into multiple pieces that drifted apart over the following years. By its 2011 return, Comet 73P had shattered into more than 60 identified fragments, creating a sprawling debris field stretching thousands of kilometers along its orbit. Some fragments remained active, generating small comas, while others lay dormant, their volatiles exhausted or locked beneath inactive crusts. These fragmentation events are crucial for assessing and predicting potential space hazards. A solitary large comet nucleus presents minimal risk to Earth, as the chance of a few kilometer-wide body striking our planet is incredibly slim. However, when a comet fragments, it spawns dozens or even hundreds of smaller pieces, each capable of entering the atmosphere. Although these fragments are individually smaller and less catastrophic than the original nucleus, their sheer number raises the likelihood that at least one will cross Earth's path. Most comet fragments harmlessly blaze out in the atmosphere or bypass Earth altogether. Yet the risk landscape shifts dramatically when facing dispersed debris instead of a lone object. Foreshadowing the 60 comet event, destined to be the brightest comet spectacle of the century, casts current observations into sharp perspective. Comets are the solar system's chaotic clockwork, arriving unpredictably, flaring with erratic brilliance and shattering without warning. They mark time in human consciousness, unlike the steady rhythms of planets and stars. One generation recalls Halley's Comet in 1986, a view that disappointed many, but left a lasting cultural imprint. The generation before witnessed Comet Hale-Bopp in 1997, dazzling the naked eye for months and shining bright enough to be seen from city centers. Today's generation might remember Lemon Swan or Three-Eye Atlas, if any of them endure and blaze with enough brilliance. Are we currently in a cluster period of unusual comet appearances? Statistical analyses of comet discovery rates over decades reveal fluctuations that could indicate genuine clustering, or they might merely mirror advances in detection technology. With more telescopes sweeping wider skies at ever greater sensitivities, it's only natural that more comets are being found. The ATLAS survey, which discovered 3 of the ATLAS comets, was designed specifically to detect near-Earth objects with comets as a fortunate bonus. Alongside it, the Catalina Sky Survey, Mount Lemmon Observatory, and Pan-STARRS in Hawaii all operate automated systems that vigilantly scan the skies for anything in motion. And since comets move, they inevitably get spotted. But there's a tantalizing hint in the data that the Oort cloud, the distant reservoir of comets, might undergo perturbations that send showers of comets plunging toward the inner solar system. Passing stars, gravitational tugs from giant molecular clouds in the galaxy, and even the solar system's vertical oscillation through the galactic plane as it orbits the Milky Way's center, all these forces could shake comets loose. If real, these comet showers would unfold over timescales of millions of years, far too vast for direct human observation. Yet hidden within the geological record traces of clustered impacts might reveal these ancient storms of comets that pummeled the inner solar system during the reign of the dinosaurs or even earlier in Earth's history. Comets serve as the solar system's chaotic clock, precisely because they defy the regular, predictable paths that planets follow. While most planets travel along nearly circular orbits, allowing their positions to be calculated centuries ahead, with remarkable accuracy, comets emerge from the outer darkness on highly elliptical trajectories. Their return times, if they return at all, span decades, centuries, or even millennia. Some are newcomers, first-time fallers from the Oort cloud, Others are short-period comets captured by Jupiter's gravity into orbits that bring them back every few years. They remind us that the solar system is not a clockwork mechanism of perfect orbits, but a dynamic, chaotic arena where gravitational forces constantly reshuffle trajectories and new players arrive without warning. Part 8. The Unbreakable Signal. While astronomers scan the skies for comets and monitor the solar wind, another cosmic race unfolds in laboratories and ground stations here on Earth. In 2025, China announced the completion of the world's longest quantum communication link, a 12,900-kilometer network connecting Beijing to distant ground stations via satellite relays, and claimed the system offers effectively unhackable data transmission. The announcement represents a milestone in the quantum information revolution. If the system performs as advertised, it will reshape the landscape of global communications and cybersecurity in ways that reach far beyond immediate military or commercial applications. At its core, quantum key distribution exploits fundamental principles of quantum mechanics to detect any attempt at eavesdropping. The basic principle is as elegant as it is strange. Information is encoded in the quantum states of photons, single particles of light, transmitted through optical fibers or across the space between satellites and ground stations. The quantum no-cloning theorem guarantees that these states cannot be perfectly copied. Any attempt to measure or intercept the photons inevitably disturbs them in ways that can be detected. This allows two parties sharing a quantum communication channel to generate encryption keys and be absolutely certain if anyone tried to intercept those keys during transmission. The process begins with entangled photons, pairs of particles created simultaneously sharing a quantum connection so that measuring one photon instantly influences the other no matter the distance between them. This phenomenon, famously dubbed spooky action at a distance by Einstein, has been confirmed through countless experiments and underpins several emerging quantum technologies, including quantum computing and quantum teleportation. For quantum key distribution, entangled photons enable two parties to establish shared random numbers that serve as encryption keys. Implementing this hardware demands extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximum fidelity. Optical systems must align satellite transceivers with ground stations across hundreds or even thousands of kilometers, all while compensating for atmospheric turbulence, satellite motion, and Earth's rotation. Single photon detectors must register individual particles arriving at rates of thousands or even millions per second, distinguishing genuine signals from background noise and detector dark counts. Error correction protocols handle inevitable imperfections while still ensuring security. China's system relies on the Michus satellite launched in 2016 and named after an ancient Chinese philosopher. Orbiting at roughly 500 kilometers altitude, the satellite follows a sun-synchronous path that provides regular communication windows over ground stations. During each pass, lasting several minutes, it distributes entangled photons to pairs of ground stations, enabling them to establish shared encryption keys. These keys then secure conventional data transmission through standard encryption algorithms with the quantum channel, ensuring the keys themselves remain uncompromised. The recent expansion to 12,900 kilometer marks a significant engineering breakthrough, surpassing earlier demonstrations that covered shorter distances or depended on trusted relay stations, which theoretically could be vulnerable. The new system links quantum channels across multiple satellite passes and ground stations, establishing end-to-end security on a continental scale. According to Chinese researchers, the network already serves government and financial institutions, safeguarding communications against both present and future decryption threats. And that last point is crucial. Current encryption systems, those protecting everything from bank transactions to classified government communications, depend on mathematical problems that are computationally hard for classical computers to solve, such as factoring large numbers or computing discrete logarithms. These tasks demand such immense computational time that breaking encryption is practically impossible even with the fastest supercomputers today. But quantum computers, if scaled up sufficiently, could solve these problems efficiently, rendering current encryption methods obsolete. Data encrypted now and intercepted by adversaries could be decrypted years or decades later, once quantum computers reach maturity. Quantum key distribution offers protection against this harvest, now decrypt later threat, because its security is rooted not in computational difficulty, but in fundamental physics. Western nations, especially the United States and European countries, watch China's advances in quantum communications with growing concern. The MIT Technology Review Quantum Index in 2025 ranks China ahead in several quantum technology metrics, including quantum communications and quantum sensing. Meanwhile, American research programs are striving to catch up, backed by Department of Energy funding quantum network test beds and DARPA's exploration of space-based quantum communication architectures. But China's early lead, fueled by substantial government investment, has created a quantum gap that alarms defense planners and technology strategists alike. The policy implications reach far beyond mere technological rivalry if quantum communication networks become the backbone of future secure communications. Nations lacking access to this technology risk facing a significant information disadvantage. International agreements governing quantum technology development remain absent. Questions about export controls, technology transfer, and standardization are still unresolved. Some researchers advocate for open collaboration and the shared development of quantum networks as global infrastructure, much like how the Internet evolved into an international resource. Others push for competitive advantage and restricted access, viewing quantum superiority as a strategic asset too valuable to share. Could space-based quantum networks become the backbone of the future Internet? The vision involves constellations of quantum satellites, providing global coverage, ground stations in every major city, and quantum repeaters extending the range beyond direct line-of-sight limits. Data would travel encrypted with quantum keys that refresh continuously, immune to interception, and resistant even to future technologies we haven't yet imagined. This system would integrate seamlessly with existing fiber optic networks, creating a hybrid classical quantum infrastructure, where quantum channels distribute keys and classical channels carry the bulk of the data. Conspiracies naturally arise around technologies this advanced and this secretive. Quantum key distribution systems demand extensive testing and calibration, producing data on photon transmission statistics, detector efficiency, and error rates. Yet most of this information remains classified or proprietary. Chinese publications describe the system's capabilities in broad terms, but omit the engineering details needed for independent verification or replication. Western intelligence agencies undoubtedly monitor the program closely, using signals intelligence and other methods to assess its true capabilities against public claims. This opacity fuels speculation about whether the system functions as advertised or if undisclosed vulnerabilities exist. Some are particularly concerned about the potential for state surveillance, fearing the system could be used to monitor or control communications on a global scale. A government controlling a nationwide quantum communication network would have unprecedented power to monitor who communicates with whom, even if the content remains encrypted. Metadata. The information about communication patterns, rather than the content of the messages, often reveals as much, if not more, than the messages themselves. This raises significant concerns about privacy and state surveillance. Traffic analysis has the power to uncover social networks, monitor movements, and predict behavior with astounding precision. Imagine a quantum network that logs every connection, every photon transmission, and every key generation event, forming a surveillance infrastructure of unprecedented scale. This concept aligns closely with the Three-Eye Atlas narrative, drawing an intriguing parallel between the two. Just as comets deliver messages from distant star systems, encoded not in language, but in chemical signatures and isotope ratios, humans are now constructing systems to carry unbreakable encoded messages across our own planet. Both serve as vessels for information that endures even the most hostile environments. Comet chemistry survives the vacuum of interstellar space and the intense heat of the sun, while quantum keys endure the efforts of active adversaries attempting to intercept them. Both push the limits of what's possible. Comets, as natural carriers of information, have been shaped by billions of years of cosmic physics. Quantum networks, as human-engineered carriers, have evolved over decades of precise innovation. Yet countless unknowns still remain, each one presenting new challenges and discoveries waiting to unfold. Current quantum key distribution rates, typically measured in kilobits per second, lag far behind the blazing speeds of classical communication, which are measured in gigabits or even terabits per second. To scale quantum networks to handle internet-level traffic, we'll either need significant breakthroughs in photon transmission and detection efficiency, or we'll have to explore entirely new approaches to quantum networking. Decoherence, the phenomenon where quantum properties are lost due to interactions with the environment, imposes fundamental limits on how long quantum states can be preserved and how far they can be transmitted. Satellites offer a solution by operating in the vacuum of space above much of the atmosphere, extending the range. However, atmospheric turbulence at ground stations continues to degrade performance, presenting an ongoing challenge. Endpoint security introduces another significant challenge. While quantum key distribution ensures the secure transmission of keys, these keys must eventually be used by classical computers to encrypt and decrypt data. If those computers are compromised, whether through malware, physical access, or side-channel attacks that exploit electromagnetic emissions or power consumption, then even the most secure quantum keys become meaningless. Ultimately, security is only as strong as the weakest link in the chain. In any real system, weak links are bound to proliferate. The quantum space race narrative reflects a deeper truth about human nature and technological progress. We compete even when it comes to understanding and harnessing the fundamental laws of physics. Quantum mechanics, perhaps the most successful physical theory in terms of predictive accuracy and technological impact, transforms into a weapon in geopolitical competition as nations vie to unlock its full potential for power and influence. The very quantum principles that reveal the secrets of atomic structure and chemical bonds are now safeguarding our communications and unlocking the door to groundbreaking computing power. Nations are pouring billions into quantum research, not merely driven by scientific curiosity, but because the future of military dominance and global economic leadership may hinge on the advancements of quantum technology in the decades to come. As the race intensifies, unanswered questions loom. Does competition fuel innovation more rapidly than collaboration? Will the benefits of quantum networks be distributed globally, or will they remain concentrated in a handful of technologically advanced nations? These uncertainties persist, even as the race accelerates. Part 9. The Circular Economy Within You. Science occasionally uncovers discoveries so startling, so against the grain of intuition, that they compel us to rethink the very foundations of what we believe is possible. The revelation that synthetic biologists have engineered yeast to transform human urine into bone mineral hydroxyapatite is one such groundbreaking discovery. The potential applications of this discovery span across medical, ecological, and even industrial fields, while its deeper implications challenge our understanding of waste value and the incredible adaptability of biological systems. By reprogramming these systems, one substance can be transformed into another in ways previously unimaginable. Urea, the primary nitrogen-containing compound in urine, serves as a waste product in mammalian metabolism, yet it now holds the key to this innovative transformation. When proteins break down in the body, amino acids are metabolized, and the nitrogen they contain must be excreted. Aquatic animals have a simple, energetically inexpensive solution. They excrete ammonia directly, which is easily diluted and carried away by water. However, land animals face a more significant challenge. While ammonia is toxic and accumulates quickly, water conservation is crucial. As a result, terrestrial animals evolved more sophisticated methods for waste excretion. Birds and reptiles excrete uric acid, a relatively insoluble compound that precipitates out and can be expelled as a paste-reducing water loss. Mammals, on the other hand, produce urea which is soluble enough to be transported in water, but less toxic than ammonia. This results in liquid urine, a compromise that balances water conservation with efficient waste removal. Humans typically produce between 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing approximately 20 to 30 grams of urea. Over the course of a year, this adds up to about 10 kilograms of urea per person. With a global population of 8 billion people, this results in around 80 million metric tons of urea being excreted annually. Currently, this urea either enters sewage systems, is broken down by bacteria, or is released into the environment. The new synthetic biology approach explores whether this waste stream could be converted into something valuable. Hydroxyapatite, the mineral component of bones and teeth, is a calcium phosphate compound with the formula Ca10PO4,6OH2. It provides bones with the hardness and structural integrity necessary to support body weight and protect organs. Natural bone is a composite material with hydroxyapatite crystals embedded in a collagen protein matrix. This combination merges the hardness of the mineral with the flexibility and toughness of organic fibers. For medical applications, pure hydroxyapatite is required for bone grafts, dental implants, and reconstructive surgeries. Currently, hydroxyapatite is synthesized through chemical processes or harvested from animal bones, but both methods face limitations in terms of purity, crystal structure, and production costs. The engineered yeast approach, however, presents a promising alternative through metabolic pathway engineering. Researchers have identified the series of enzymatic reactions required to convert urea into the chemical precursors of hydroxyapatite and have successfully inserted the genes encoding these enzymes into yeast cells. The yeast Saccharomyces cerevisiae, commonly used in brewing and baking, now carries synthetic metabolic pathways that don't naturally exist. When fed urine as a nitrogen source, along with calcium and phosphate ions, these engineered yeast cells produce hydroxyapatite crystals. These crystals then precipitate out of the solution, allowing them to be harvested efficiently. The mechanism behind this process involves multiple steps. Urease-UR's enzyme breaks urea into ammonia and carbon dioxide. The ammonia is then incorporated into amino acid synthesis pathways, while the carbon dioxide, along with additional calcium and phosphate ions, undergoes mineralization reactions that form hydroxyapatite. The crystallography of the resulting hydroxyapatite, its size, shape, and purity, depends on various reaction conditions, including pH, temperature, ion concentrations, and the genetic programming of the yeast pathways. Early results show promise with hydroxyapatite produced that exhibits properties similar to bone mineral. However, significant optimization is still needed before the process can be applied in medical applications. Currently, the efficiency and yield rates of this process limit its immediate viability. The yeast produces hydroxyapatite at concentrations too low for commercial use, meaning that large bioreactor volumes are required to generate meaningful quantities. Further improvements in efficiency and scaling are necessary to make this process commercially viable. Purification challenges arise because hydroxyapatite must be separated from yeast cells, growth medium components, and metabolic byproducts. Purity is crucial for medical applications, as any foreign proteins or bacterial endotoxins in implanted hydroxyapatite could trigger immune responses or infections. Achieving medical-grade purity from a biological production system necessitates rigorous quality control and purification protocols. Despite these hurdles, the potential for this technology is transformative. Bone fractures affect millions of people every year. While most fractures heal naturally, complex fractures or bone loss due to disease or trauma often require grafts or synthetic materials to support healing. Current bone graft materials include autografts harvested from the patient's own body, allografts from cadavers, and synthetic ceramics. Each of these options has its drawbacks. Autografts require additional surgery to harvest the graft tissue, increasing the risk of complications. Allografts carry small risks of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate well with natural bone, limiting their effectiveness. Hydroxyapatite produced biologically from waste materials could offer an abundant, cost-effective alternative if the challenges of production and purification are addressed. One major market for this material is dental implants. Hydroxyapatite coatings on titanium implants significantly improve osseointegration, which is the bonding between the implant and the jawbone. Currently, these coatings are made using hydroxyapatite, produced through high-temperature chemical processes, which are energy-intensive. In contrast, biological production at room temperature in aqueous solutions would not only reduce energy costs and the carbon footprint, but could also lead to the creation of more bone-like crystal structures that integrate better with living tissue. The ecological benefits of this process extend beyond the direct use of the material itself, offering a more sustainable and environmentally friendly alternative. Urea in wastewater contributes to eutrophication when released into rivers and coastal waters. Excess nitrogen from urea stimulates algal growth, leading to blooms that deplete oxygen and create dead zones. Capturing urea and converting it into solid mineral hydroxyapatite removes nitrogen from the wastewater stream, reducing its environmental impact. This process embodies waste valorization, the principle of treating waste as a resource rather than a disposal problem. However, controversies inevitably arise around using human waste in medical materials. Cultural taboos surrounding urine and feces are deeply ingrained. Despite this, intellectually, we understand that purified compounds have no memory of their origin. The calcium atoms in hydroxyapatite produced from urine are chemically identical to calcium atoms from any other source, illustrating that the source of the material is irrelevant to its purity and functionality. Once purified, the material carries no trace of waste beyond the historical fact of its production pathway. However, psychological resistance remains. Would patients accept bone grafts or dental implants produced from urine? Would regulatory agencies approve such materials for human use? These questions are less about technical feasibility and more about cultural values and risk perception. One of the most compelling use cases for this technology could be in space exploration. Astronauts on Mars missions or long-duration space flights face extreme resource constraints, making every recycling opportunity invaluable. Crew members will produce urine daily, and this urine contains nitrogen and other elements that must be processed, either recycled or disposed of. The ability to convert urine into valuable materials such as hydroxyapatite for medical applications could provide a sustainable solution in these environments where traditional resources are scarce. Converting urine into usable hydroxyapatite for medical purposes or structural materials, effectively kills two birds with one stone. It manages waste while producing valuable products. The closed-loop life support systems necessary for space exploration push designers toward maximal recycling and minimal waste, where every resource counts. In such a system, your waste could literally save your life. If a bone fracture occurs on Mars, and the only available hydroxyapatite is produced from crew urine, it could provide the critical material for a life-saving graft. However, resistance from the pharmaceutical and medical device industries to circular biotechnology adoption represents a predicted, rather than demonstrated, conspiracy. These industries profit from the current production methods and established supply chains. Disruptive technologies that threaten existing business models often face resistance regardless of their technical potential or merit. Whether resistance to urine-derived hydroxyapatite materializes depends on several factors, including production costs, scalability, regulatory pathways, and intellectual property landscapes. If the technology can be patented and controlled by established players, adoption is more likely. However, if it threatens to commoditize a high-margin product, resistance from the industry becomes more probable. The deeper takeaway extends beyond any single application. Nature wastes nothing. Nutrients cycle through ecosystems, with one organism's waste becoming another's food. Energy flows and elements circulate. Humans evolved in cultures where waste disposal was simpler, as population densities were low and natural processes could break down and recycle most waste products. However, industrialization and urbanization disrupted these cycles, creating waste streams that overwhelm natural recycling systems. Synthetic biology offers a potential solution, providing tools to rebuild these cycles artificially. By engineering organisms to fill ecological niches that don't exist in nature, but serve human needs, we can begin to restore some of the balance lost in modern society's waste management systems. Transforming urine into bone mineral is just one fascinating example of what we're achieving. The same innovative principles are now being applied to convert carbon dioxide into fuel, plastic waste into biodegradable polymers, and agricultural runoff into valuable chemicals. We're beginning to close the loops that our technological advancements once opened, catching up to the circular economy that nature has perfected over billions of years. Part 10. The yawn that crosses. Species animal behavior has always captivated us because it offers a mirror to our own cognitive and emotional states, yet it unfolds in creatures whose minds remain enigmatic. Contagious yawning, the curious phenomenon where seeing someone yawn triggers an uncontrollable urge to do the same, was once thought to be confined to humans and a select few highly social mammals like chimpanzees and dogs. However, a groundbreaking study revealing contagious yawning in zebrafish has upended this belief, raising intriguing questions about the evolutionary origins and neural mechanisms that underpin this behavior. Zebrafish, small freshwater creatures native to South Asian rivers and commonly found in both scientific labs and home aquariums, have long been used as model organisms for exploring vertebrate development and behavior. This discovery opens up a whole new dimension to our understanding of how yawning might bridge species. Zebrafish embryos are transparent, offering researchers a unique advantage. They can observe organs forming in real time under microscopes. Their genetics are well documented, and a variety of tools exist for manipulating genes and studying the outcomes. These fish are small, inexpensive to maintain, and reproduce prolifically, making them perfect for large-scale experiments. Yet no one anticipated that they would exhibit contagious yawning. In the experiment, zebrafish were placed in adjacent tanks, separated by transparent walls, allowing them to see each other. Yawning was triggered in one fish through oxygen deprivation, a known yawning stimulus across many species. Cameras then recorded the behaviors of both the yawning fish and those observing revealing an unexpected reaction that would challenge conventional understanding of this peculiar phenomenon. The analysis revealed that observer fish yawned significantly more frequently after watching a neighboring fish yawn, with the timing showing a clear correlation suggesting genuine contagion rather than mere coincidence due to shared environmental factors. So why is this discovery so surprising? Contagious yawning was previously believed to require the presence of mirror neurons or similar neural circuit structures that enable an animal to mentally simulate the actions and emotional states of others. These circuits primarily concentrated in the brains of primates and suspected in some social mammals form the neural foundation for empathy, imitation learning, and theory of mind. However, fish brains lack the cortical structures where these mammalian mirror neurons reside. Their neural organization is fundamentally different, simpler in some ways, yet undoubtedly sophisticated in its own right. This raises profound questions about the mechanisms behind contagious behavior and whether simpler brains can still harbor such complex phenomena. The discovery of contagious yawning in zebrafish suggests that the behavior either doesn't require the complex neural machinery we once thought, or that convergent evolution has led to the development of similar neural circuits in fish through entirely different anatomical pathways. The neural circuits responsible for yawning in any species remain only partially understood. Yawning itself involves the coordinated contraction of muscles in the jaw, face, throat, and respiratory system, producing the signature wide mouth opening, deep inhalation, and slow exhalation. Once triggered, the behavior seems to be involuntary and difficult to suppress, even in social contexts, where yawning might be considered inappropriate. This resistance to conscious control underscores the deeply ingrained automatic nature of the action, adding another layer of intrigue to its evolutionary purpose and neural underpinnings. Yawning can be triggered by a variety of factors, including fatigue, boredom, low oxygen levels, and the sight of others yawning. The existence of these diverse triggers suggests that multiple neural pathways may converge to produce a common motor output. In humans, contagious yawning tends to increase during childhood development peaks in young adulthood and shows a notable correlation with measures of empathy. Research has shown that people who score high on empathy questionnaires tend to yawn more readily when they observe others yawning. Conversely, individuals with autism spectrum disorders who often experience difficulties with social cognition and empathy demonstrate reduced contagious yawning. These findings lend support to the hypothesis that contagious yawning is linked to neural systems responsible for social cognition and emotional resonance, reinforcing the idea that this behavior is deeply connected to our ability to understand and share the emotions of others. Discovering the same behavior in zebrafish creatures. We don't usually associate with empathy or complex social cognition challenges this tidy narrative. The evolutionary puzzle becomes even more intriguing when we consider its taxonomic range. Contagious yawning is now observed in humans, chimpanzees, bonobos, dogs, and unexpectedly zebrafish. It's notably absent or hasn't been observed in many species that have been tested, including cats, horses, and most birds. This patchy distribution across the animal kingdom raises the possibility of either multiple independent origins of the behavior or a singular ancient origin that has since been lost in many lineages. Yet neither explanation fully satisfies the puzzle. The idea of contagious yawning evolving independently in both mammals and fish seems improbable unless the behavior serves an essential function we haven't yet identified. If it has an ancient origin, then we're left to explain why so many species have lost it over time. Theories about its purpose vary significantly. One suggestion posits that contagious yawning plays a role in group coordination, helping synchronize states of arousal or attention within social groups. If one individual detects a shift in environmental conditions that triggers yawning, perhaps signaling a transition from alertness to rest. Spreading that signal throughout the group could help synchronize collective behavior. Fish schools, for example, clearly rely on such coordination for survival and movement. Fish move as cohesive units, turning in perfect synchrony, maintaining precise spacing, and executing coordinated, evasive maneuvers in response to threats. Could contagious yawning be a behavioral tool that facilitates this kind of coordination? Another hypothesis suggests yawning might help alleviate stress and foster social bonding. It could play a role in regulating stress hormones or resetting neural states during moments of social tension. Witnessing others yawn and responding with a yawn could trigger a feedback loop that helps groups collectively manage tension. Zebrafish, being social creatures that naturally school together, experience complex social dynamics involving dominance, hierarchies, mate competition, and predator vigilance. It's possible that contagious yawning serves a crucial role in maintaining group cohesion, particularly in stressful situations. The controversy lies in whether the behavior seen in zebrafish truly qualifies as yawning or if it's simply another jaw movement or gill action misclassified as such. Since fish don't breathe air under normal circumstances, the respiratory aspect of mammalian yawning has no direct counterpart in their behavior. The gaping mouth movement observed in zebrafish could serve various physiological functions, such as gill ventilation or feeding. Critics argue that without clear evidence showing the fish behavior shares the same neural triggers and physiological consequences as mammalian yawning, labeling it as contagious yawning risks anthropomorphizing a behavior that may look similar on the surface but is functionally distinct. Proponents counter that the behavior in zebrafish shares key features with mammalian yawning, including its involuntary nature, stereotyped motor pattern, and its triggering by hypoxia, along with the newly demonstrated social contagion. While the neural pathways may differ between fish and mammals, this could be due to the hundreds of millions of years of evolutionary separation, suggesting that the underlying function could still be fundamentally similar. However, if the behavior serves similar functions and responds to similar triggers, then the term yawning could be legitimately applied. Biology is full of examples of convergent evolution where different structures evolve to serve similar functions. For instance, bird wings and bat wings are anatomically distinct, but serve the same function of flight. Similarly, if zebrafish exhibit a behavior that aligns functionally with yawning, the term could be justifiably used despite the differences in anatomy and neural pathways. Perhaps fish yawning and mammalian yawning represent convergent solutions to similar behavioral or physiological challenges. This speculation ventures into deeper biological territory. Could yawn contagion be a universal signal, an ancient communication channel that predates more complex social cognition? It's possible that the basic neural circuitry responsible for making yawning contagious evolved early in vertebrate history, preserved across hundreds of millions of years because it serves fundamental coordination functions in social species. This shared mechanism might be one of the oldest forms of social communication, helping groups synchronize behavior for survival. For this theory to hold, the behavior would need to offer significant fitness benefits, improving survival or reproduction, enough that natural selection would preserve it despite the costs of the neural machinery required. There's a fringe possibility rarely discussed in formal academic settings, but quietly murmured in conference hallways. Could synchronization phenomena extend beyond individual species, perhaps even across entire kingdoms of life? This provocative idea suggests that the capacity for coordinated behavior might be a fundamental trait, shared across different forms of life, unlocking new insights into the deeper connections between species. Yawn contagion, as we currently grasp it, spreads through sensory perception. Witnessing or hearing a yawn sparks neural pathways that prompt us to yawn in response. Yet nature's broader synchronization unfolds through mechanisms we're only starting to unravel. Heart cells pulsing in unison within a culture align their rhythms through intricate electrical and chemical signals. In the lush mangroves of Southeast Asia, fireflies orchestrate a mesmerizing spectacle, their flashes pulsing in perfect harmony across hundreds of individuals. Could this breathtaking synchrony hint at profound biological principles of resonance echoing in phenomena like yawn contagion? This captivating narrative weaves cosmic themes exploring how resonance and synchronization ripple across scales, connecting the smallest organisms to the grandest universal patterns. Schools of fish glide in perfect harmony, their movements synchronized as they respond to subtle shifts in water pressure detected by their lateral line sensors. Similarly, flocks of birds wheel and turn as one, each bird instinctively adhering to simple rules of spacing and alignment, weaving together to create mesmerizing, intricate patterns that emerge from their collective dance. On grand cosmic scales, planets dance in resonant orbits, their periods bound by gravitational harmony into precise integer ratios. Jupiter's moons, Europa, Ganymede, and Io, perform a captivating 4-2-1 resonance, their orbital patterns repeating with mesmerizing precision. Across the vastness of space, galaxy clusters glide under the pull of mutual gravitation, their intricate dynamics intertwined over millions of light years. Synchronization emerges as a universal force, orchestrating systems from the molecular to the cosmic. Oscillators, be it neurons sparking hearts, pulsing pendulums swaying, or planets tracing their celestial paths, naturally align when linked, their rhythms converging into shared frequencies. The mathematics of coupled oscillators unveils striking parallels, uniting vastly diverse physical systems in a symphony of harmony. Yawn contagion might be a vivid biological echo of universal synchronization principles, acting as a social oscillator that binds us through observation, sparking phase-locked responses. Human brains and distant stars may share deeper kinship than we imagine when we view them through the lens of abstract principles rather than specific mechanics. Both are intricate, dynamical systems woven with internal structures, emergent behaviors, and intricate couplings to their external worlds. Both brains and stars process information, albeit through wildly distinct methods and on vastly different scales. Brains handle sensory inputs and produce behavioral outputs via electrochemical signals coursing through neural networks. Stars, meanwhile, transform gravitational inputs into radiant outputs through nuclear fusion, governed by the delicate balance of hydrostatic and thermal equilibrium. The analogy falters if stretched too far, yet it points to profound questions about complexity, information, and cosmic organization. The zebrafish study underscores our limited grasp of animal minds and behaviors. Every assumption, every so-called established fact about what animals can or cannot do remains tentative, open to upheaval with fresh evidence. We once believed contagious yawning hinged on empathy and mirror neurons. Fish clearly didn't get the memo. Behaviors we deem uniquely human or mammalian may have deeper origins or wider reach than we suspect. Tool use surfaces in birds and octopuses, defying old assumptions. Culture-learned behaviors passed socially across generations thrives in whales and crows. Metacognition. The act of thinking about thinking reveals glimmers in rats and dolphins. The deeper we probe, the more those rigid lines we etch between humanity and the animal kingdom, between intricate minds and rudimentary ones, dissolve under the weight of revelation. Part 11. The Stone That Will Skim Earth's Atmosphere. April 13, 2029 will be a date humanity remembers, assuming we're still here to remember things. On that fateful day, asteroid 99942 Apophis, named for the ancient Egyptian demon of chaos and darkness, will streak perilously close to Earth, just 31,000 kilometers away. For scale, geostationary satellites circle at about 35,000 kilometers. Apophis will plunge inside the vital ring of satellites, powering weather forecasts, global communications, and GPS navigation. Apophis will blaze as a vivid point of light, racing across the starry sky, visible to the naked eye. It marks the first time in recorded history that an asteroid of such magnitude has swept so near Earth, close enough for casual stargazers to witness its passage. Current orbital calculations confirm no risk of impact. The close approach of Apophis is a certainty, its geometry meticulously mapped, yet its trajectory will sweep it safely past Earth without collision. This confidence stems from decades of painstaking observation and orbital refinement. When Apophis was first spotted in 2004, early calculations hinted at a slim but unsettling chance of impact in 2029, sparking fleeting public panic and fervent scientific scrutiny. Further observations as Apophis traced different arcs of its orbit sharpened the calculations, steadily shrinking. The uncertainty ellipsed the zone where the asteroid could be at any moment until the possibility of a 2029 impact was entirely eliminated. Yet the tale doesn't conclude in 2029. The close encounter will reshape Apophis's orbit through Earth's gravitational tug. As an asteroid sweeps near a planet, tidal forces and gravitational acceleration reshape its trajectory, often with dramatic flair. The extent of this shift hinges on the proximity of the approach and the relative velocities involved. Apophis will endure substantial orbital deflection, altering its solar period and recalibrating its potential for future Earth encounters. Forecasts for Apophis's later close approaches in 2036 and 2068 carry greater uncertainty as their outcomes hinge on the precise dynamics of the 2029 encounter, details we can't fully measure until it unfolds. This rare passage closer than geostationary orbits offers an unparalleled scientific opportunity. Telescopes will relentlessly track Apophis as it nears, capturing its rotation, mapping its surface features, analyzing its composition via spectroscopy, and gauging its size and shape with radar. Spanning roughly 370 meters in diameter, Apophis is massive enough to unleash regional devastation if it ever struck, yet small enough that discerning surface details from Earth-based observations remains a formidable challenge. Apophis's close flyby brings it within range of techniques typically reserved for near-Earth objects during even tighter approaches. Radar astronomy will be pivotal. Radio telescopes such as the Goldstone antenna in California and the Arecibo replacement facility, if operational by then, will ping radio waves off the asteroid's surface, decoding the echoes to reveal intricate details. Radar delivers pinpoint precision, measuring distances to within meters, rotation periods to within seconds, and surface roughness with detail unmatched by optical telescopes. Delay Doppler radar imaging crafts two-dimensional portraits with one axis charting distance, unveiling the asteroid's secrets in vivid clarity. The echo's time delay maps distance, while the Doppler shift tracks velocity, crafting radar images that unveil Apophis's shape, rotation, and surface features, sometimes resolving boulders, craters, and ridges mere meters wide. Rotation studies are key as an asteroid's spin reveals its past. Apophis currently spins with a roughly 30-hour period gleaned from light curves that capture brightness shifts as its facets reflect sunlight toward Earth. Though stable now, this rotation will shift during the 2029 Earth encounter. Tidal forces from Earth will tug at Apophis during its close pass, potentially accelerating or decelerating its rotation based on the encounter's geometry. Measuring this rotational shift will yield clues about the asteroid's internal makeup, whether it's a solid monolith or a loosely bound rubble pile of smaller fragments held together by gravity. The Yarkovsky effect weaves yet another layer of intricacy. Asteroids soak up sunlight, heating their surfaces, then emit that energy as infrared radiation. This thermal emission carries momentum, acting like a subtle rocket thrust. For a spinning asteroid like Apophis, the warmer afternoon side radiates more heat than the cooler morning side, generating an asymmetric force that either accelerates or decelerates its orbit, depending on whether its rotation is prograde or retrograde. Over millions of years, this Yarkovsky effect can dramatically reshape an asteroid's path, nudging its trajectory in profound ways. The Yarkovsky effect subtly drives asteroids from the main belt into Earth-crossing paths. For Apophis, precisely measuring this effect is crucial to forecast its long-term orbital journey. Though minuscule, causing mere meters of orbital shift per year, these tiny nudges compound over decades, amassing into kilometers of positional uncertainty. The 2029 close approach offers a prime chance to measure the Yarkovsky effect by comparing Apophis's actual position with predictions excluding thermal influences. Any deviation reveals the Yarkovsky's subtle push, enabling fine-tuning of models to forecast future encounters with greater precision. Public perception poses both a challenge and an opportunity. Since its discovery, Apophis has fueled sensational news headlines, often laced with dire warnings of killer asteroids and cosmic perils. Yet the actual risk remains low to negligible for all calculated encounters. Communicating this risk effectively, however, remains a formidable task. Explaining a 1 in 45,000 chance of Apophis impacting Earth in 2068 carries varied weight. To statisticians, it's a negligible risk, dwarfed by everyday hazards we routinely accept. Yet to those unversed in probability, 1 in 45,000 feels alarmingly tangible, hinting at a real threat rather than a near-impossible event. Within the planetary defense community, proposals for Apophis missions have sparked lively discussion, aiming to deepen our understanding and refine our preparedness. Dispatching a spacecraft to rendezvous with Apophis during or after its 2029 Earth flyby would yield intimate data unattainable from Earth. Such a mission could meticulously map the asteroid's composition, internal structure, and surface features, unveiling secrets hidden from distant observations. A mission to Apophis could also showcase deflection technologies, such as kinetic impact or a gravity tractor, to subtly shift its orbit, proving humanity's ability to shield Earth from future asteroid threats. NASA's DART mission, which successfully struck the asteroid Dimorphos in 2022, demonstrated that kinetic deflection performs as predicted, paving the way for such bold endeavors. The impact altered Dimorphos's orbit around its larger companion Didymos, proving humanity can redirect asteroid paths with enough lead time. An Apophis mission would expand on DART's triumph, testing deflection techniques on a larger, scientifically richer target, pushing the boundaries of planetary defense. Conspiracy theories claiming NASA downplays. Apophis's impact odds are predictable yet baseless, though their psychological roots are clear. Space agencies tread a fine line between transparency and preventing panic. Sharing every preliminary orbital calculation laden with large uncertainties risks sparking widespread alarm. Large uncertainties are par for the course with newly discovered objects and sparse observational data, yet waiting for refined calculations before public announcements invites accusations of cover-ups if independent discoveries or leaks surface. NASA and other agencies lean toward transparency, sharing orbit calculations and impact probabilities via the Sentry system and Torino scale. Still, transparency doesn't shield them from conspiracy theories. Conspiracy theories merely pivot from claims of hidden impacts to tales of deflection failures or alien meddling. The narrative of an asteroid grazing Earth's atmosphere captures a thrilling blend of peril and awe. Such close approaches ignite wonder and inspire profound curiosity. Apophis won't strike Earth, but its close brush will make its presence undeniable, a fleeting spectacle as we witness a mountain-sized rock skim our cosmic neighborhood. This near pass underscores that space is far from empty. Remnants of solar system formation still whirl out there, sometimes crossing Earth's path. While luck has spared us thus far, it's not eternal. Preparation is paramount. Detection, tracking, characterization, and deflection technologies form humanity's safeguard against the cosmic lottery that will one day bring an impact. Apophis's close approach offers a global, teachable moment, highlighting the need for international cooperation in planetary defense. Asteroids heed no borders. A threat to one nation imperils all. The United Nations Committee on the Peaceful Uses of Outer Space spearheads global efforts to monitor near-Earth objects and bolster response capabilities. The 2029 Apophis flyby will likely ignite fresh momentum for planetary defense funding and policy-spurring advancements in detection networks and deflection technologies. Looking forward to 2040's planetary parade offers vital context for these efforts. The universe moves to its own rhythm, heedless of human schedules. Asteroids sweep in as orbital mechanics decree. Planets align in accordance with Kepler's laws. Comets plunge from the Oort cloud, nudged by gravitational ripples set in motion millennia ago. We pencil these cosmic events onto our calendars, tracking and preparing for them, but they unfold on the unyielding terms of physics, indifferent to human convenience. Apophis will sweep past in 2029, heedless of our gaze, our concerns, or our readiness. The cosmos's indifference to human affairs is both chilling and freeing. Part 12. When Planets Dance. September 20th, 2040. Etch it onto whatever calendar endures, for on that day, the solar system will unveil a geometric spectacle rare enough to captivate yet common enough to recur with predictable rhythm. On September 20th, 2040, 6 planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, will cluster within a tight arc of the sky, their longitudes along the ecliptic spanning less than 90 degrees as viewed from Earth. The media will likely dub this a planetary alignment or parade, though the planets won't form a precise straight line. Instead, they'll gather in a striking celestial cluster visible together from Earth's night side. The geometry unfolds as follows. Planets trace their orbits around the Sun, roughly aligned in the ecliptic plane defined by Earth's own orbit. From our vantage point, they glide along a celestial path, threading through the zodiac constellations. At times, they scatter across the entire ecliptic, appearing at different hours as Earth spins. At other times, their orbits converge, clustering multiple planets in a single swath of sky, visible together in a celestial spectacle. These gatherings happen regularly, yet unpredictably, driven by the varied orbital periods of planets aligning in fleeting harmony. The rarity of a planetary alignment hinges on how many planets we include and how strictly we define their clustering. Having all 8 planets within a 90 degrees arc occurs every few decades, while squeezing them into a 30-degree band happens only every few centuries. A perfect straight-line alignment with all planets at 0° separation, as seen from the Sun, is likely impossible on human timescales, as their orbital periods lack the precise integer ratios needed for such flawless recurring convergence. The 2040 event will captivate observers as the planetary cluster features the brilliant naked-eye planets Mercury, Venus, Mars, Jupiter, and Saturn, all gleaming without need for telescopes, alongside Uranus, visible with binoculars or small scopes. Neptune, far off in its orbit, will miss the cosmic gathering. After sunset, this dazzling ensemble will rise together in the eastern evening sky, tracing an arc across the southern heavens, offering hours of viewing delight, with the spectacle's path varying by observer latitude. Amateur astronomers will revel in the 2040 event, seizing the chance to capture all visible planets in a single wide-angle photograph, crafting stunning images that unveil the solar system's grand architecture. The planets' varied brightnesses and hues add captivating visual flair. Venus shines a dazzling white, Mars glows a vivid orange-red, and Jupiter radiates a warm, yellowish white. Saturn akin to Jupiter, but subtly dimmer, glows with a pale golden hue. Uranus, just perceptible through binoculars, appears as a faint blue-green disk. Capturing them together in a single photograph paints a vivid portrait of planetary diversity, condensed into one striking frame. Professional astronomers, meanwhile, will harness the 2040 alignment for far more than aesthetic snapshots, seizing the chance to probe deeper cosmic insights. Planetary alignments spark no extraordinary gravitational effects, despite enduring myths of tidal surges or seismic triggers. Yet they offer a rare chance for simultaneous measurements across multiple planets using identical instruments and methods. Comparative planetology thrives in these moments. Observing the atmospheres of Venus, Jupiter, and Saturn within the same window minimizes instrumental and observational variables, enabling sharper, more reliable comparisons. The 2040 alignment could unveil hidden cosmic treasures. As planets cluster, the backdrop of stars in that sky region draws heightened scrutiny. Keen observers scanning for planets might spot faint asteroids, distant comets, or even undiscovered worlds lurking in the outer solar system, revealed by the intensified gaze on this celestial stage. Despite extensive searches, the enigmatic Planet 9, a hypothetical world proposed to explain the strange orbital clustering of distant trans-Neptunian objects, remains elusive. If this phantom planet truly exists, its predicted location is a slow wanderer across the zodiac. A stroke of cosmic luck may place it near a region of planetary clustering in 2040, dramatically increasing its chances of discovery, as a multitude of telescopes will already be aimed in that very direction. Throughout human history, planetary alignments have been steeped in rich mythological and cultural contexts. Ancient astronomers meticulously tracked the positions of planets, observing conjunctions and alignments with keen attention, and often attributed profound significance to these celestial events. Even today, astrological traditions enduring, despite the absence of scientific validation, continue to assign meaning to planetary configurations, drawing upon symbolism and perceived correlations that link the movements of celestial bodies to human affairs. The scientific worldview dismisses these connections as nothing more than pattern-seeking imposed on random coincidences. Yet the human psychological response to celestial alignments remains potent. When planets cluster in a single region of the sky, it carries a sense of weight and meaning, even if our intellect tells us it's merely the mechanics of orbital geometry. Inevitably, some fringe communities will predict catastrophic consequences stemming from the 2040 alignment. Planetary gravitational forces allegedly triggering earthquakes or catastrophic weather events are classic doomsday scenarios with no foundation in physics. The gravitational pull exerted by distant planets on Earth is minuscule compared to that of the Moon and the Sun. Even during planetary alignments, their combined gravitational effect produces only tiny perturbations in Earth's orbit, far too insignificant to impact geological activity or atmospheric processes in any measurable way. But facts rarely stop predictions. Somewhere online, someone will assert that the alignment will unleash disasters, and others will take them seriously, preparing accordingly. When those disasters fail to occur, the predictions will quietly fade from memory or be rationalized away. Yet beyond the hype, planetary alignments offer hidden scientific opportunities, such as precise measurements of mass distribution throughout the solar system. Precise tracking of planetary positions enables rigorous tests of gravitational theories and the fine-tuning of planetary mass estimates. Each planet exerts a gravitational influence on every other planet, producing orbital perturbations that gradually accumulate over time. By precisely measuring planetary positions and comparing them to the predictions of Newtonian gravity, astronomers can uncover anomalies that may reveal unknown masses elsewhere in the solar system, or more speculatively hint at deviations from gravitational theory itself. Meanwhile, the cultural significance of planetary alignments as global events carries weight in an increasingly interconnected world. Unlike eclipses, which can only be observed from select geographic locations, planetary configurations are visible worldwide, weather permitting. This allows shared experiences to unfold across cultures and continents. In 2040, observers in Tokyo, New York, Sydney, and Lagos will witness the same planetary arrangement, creating a moment of cosmic unity that transcends political and cultural boundaries. Metaphorically, this can be likened to a planetary choir in harmonious alignment. Each planet moves to its own rhythm. Mercury races around the Sun every 88 days, while Neptune drifts slowly, taking 165 years for a single orbit. These varying periods weave intricate rhythms and patterns over time. When planets align, it's like a fleeting moment in a vast cosmic symphony, where multiple instruments come together to play a chord before they drift apart once more, resuming their solitary melodies. The metaphor shouldn't be stretched too far, as planets don't actually produce sound or music. However, it does capture something genuine about the patterns and rhythms within orbital dynamics. Foreshadowing the 2015 supermoon adds a sense of continuity to the narrative linking past and future cosmic events. These alignment events and close planetary approaches serve as markers of time that stretch beyond individual human lifespans. A person born in 2040 will be 12 when the supermoon takes place, 20 when a Paus makes its close pass, and will be middle-aged before the next significant planetary alignment. These cosmic occurrences offer milestones in generational memory-shared experiences that shape eras and provide a framework for historical time, extending beyond human-made constructs like decades and centuries. Part 13. The Moon That Touches Earth. November 9, 2022 will witness the closest lunar approach of the 21st century, a supermoon so extraordinary it pushes the very definition of the term. The moon's orbit around Earth is not perfectly circular, but elliptical, meaning the distance between Earth and the moon fluctuates. At its closest approach, or perigee, the moon comes within about 363,000 kilometers, while at its farthest point, or apogee, it drifts about 405,000 kilometers away. This variation in distance results in noticeable changes in the moon's apparent size from Earth. When the moon reaches perigee during its full phase, appearing at its biggest and brightest, we call it a supermoon. The November 2022 supermoon will occur at an exceptionally close perigee, bringing the moon to an astonishing 356,500 kilometers from Earth's center. This brings the moon about 3% closer than typical supermoons, and around 6% closer than the average full moon. While this might sound minor in percentage terms, it's important to remember that we're dealing with angular sizes, which change non-linearly with distance. A 6% reduction in distance results in roughly a 13% increase in the moon's apparent diameter and a significant 30% boost in its apparent brightness. At its closest approach, the moon will appear so large that the size difference from average full moons becomes noticeable even without instruments. Place a full moon photograph from 2022 beside one taken at an average lunar distance, and the difference is striking. The supermoon dominates more of the sky. Its features stand out larger. Its brightness casts a more dramatic light across landscapes. Under ideal atmospheric conditions, with the moon near the horizon, the combination of its actual size increase and the moon illusion. The psychological effect that makes moons near the horizon appear larger than those overhead will produce views that feel almost surreal. Photography opportunities will be extraordinary. Lunar photographers eagerly anticipate supermoons to capture the moon alongside landscape features, using its increased size to craft dramatic compositions. The 202 event will offer the ultimate opportunity for this generation of photographers. Planning will begin years in advance, scouting locations where the moon will rise or set behind compelling foreground subjects, calculating precise timing and positioning to capture the perfect shot. The brightness boost brings consequences that extend beyond aesthetics. Moonlight in general is bright enough to cast shadows and influence nocturnal animal behavior. Supermoonlight is even brighter, potentially casting sharp, distinct shadows from objects and illuminating landscapes to levels nearing twilight. Nocturnal animals that time their activities with lunar phases may react to the unusual brightness. Predators that hunt using vision might gain an advantage over prey that depend on darkness for concealment. Prey species may adjust their behavior, remaining hidden during the brightest hours. Extreme tides represent the most significant physical consequence of close lunar approaches. Ocean tides arise from the gravitational gradient. The difference in the moon's gravitational pull on the near side of Earth, compared to the far side, creates a gradient that forms two tidal bulges, one facing the moon and one opposite. As Earth rotates, coastlines move through these bulges, generating the familiar twice-daily tidal cycle. The strength of tides depends on the moon's distance, with closer moons creating stronger gradients and therefore higher tides. Spring tides, the highest tides occurring during new and full moons when the sun and moon align, will be amplified during the 2015 supermoon. Coastal areas already experiencing high spring tides will see water levels rise several centimeters above normal. This might not sound dramatic, but at high tide during storms, those extra centimeters can mean the difference between water staying within channels or overtopping seawalls and flooding coastal infrastructure. Coastal flood warnings will likely be issued for vulnerable areas, especially those already facing sea level rise from climate change. Seismic coupling speculation enters murkier territory. Some researchers have examined statistical correlations between lunar phases and tidal forces with earthquake occurrences, searching for evidence that tidal stress on faults might trigger quakes already near failure. The mainstream consensus holds that any such effect, if it exists at all, is negligibly small. Faults fail when accumulated. Tectonic stress exceeds the friction keeping them locked. Tidal stresses are orders of magnitude weaker than tectonic stresses. However, for faults already at the threshold of failure, even tiny additional stresses might theoretically act as a trigger. Studies have found weak correlations between tides and earthquakes in some fault systems, but not in others. With effects so small, they're difficult to distinguish from statistical noise. The 2022 supermoon will serve as a natural experiment. If tidal triggering is real and measurable, we might observe slightly elevated earthquake rates globally in the days surrounding the closest approach. If earthquake rates remain normal, it will further support the conclusion that tidal effects on seismicity are negligible. Cultural responses to the supermoon will likely blend celebration and anxiety. Festivals and public viewing events will attract crowds to dark sky locations and iconic landmarks. When lunar eclipses coincide with supermoons, they become media spectacles drawing millions of viewers. Even without an eclipse, the record-setting nature of the 2052 event will capture widespread interest. At the same time, various doomsday predictions and apocalyptic interpretations will circulate online, falsely claiming that the close approach portends disasters. These predictions follow predictable patterns and will be just as predictably wrong, yet they will briefly capture attention and cause unnecessary anxiety among those unfamiliar with astronomical facts. The phrase, "the night that glowed like day," may be an exaggeration, but it captures the essence of the experience of extremely bright moonlight. Human eyes adapt to darkness, pupils dilate to gather more light, and photoreceptor cells increase sensitivity. Under full dark adaptation, the sensitivity range of human vision spans many orders of magnitude. Moonlight from a typical full moon provides enough illumination to walk comfortably read large print and perceive colors faintly. Super moonlight pushes this even further potentially, allowing for reading normal print and seeing colors more vividly. Combined with high atmospheric clarity and dark surroundings, the experience approaches the illumination level of deep twilight. Bright moonlight also benefits atmospheric scattering studies, as lunar illumination provides a stable light source for measuring atmospheric properties. Research groups studying aerosols, clouds, and atmospheric chemistry sometimes use moonlight for calibration or to extend observations beyond daylight hours. The supermoon offers unusually high signal levels, potentially enabling more precise measurements and the detection of subtle effects that typically fall below detection thresholds. Citizen science projects could coordinate global observations of the supermoon, gathering data on its apparent brightness, color, and atmospheric effects from observers around the world. Similar initiatives have successfully collected eclipse observations, meteor counts, and aurora reports, building valuable data sets that complement professional research while engaging the public's interest in astronomy. The supermoon offers an accessible target that anyone can observe and photograph, lowering barriers to participation. Transitioning to comets that may outshine even this supermoon sets the stage for the final narrative beats. While the moon at its closest approach will be spectacular, it is a regular phenomenon, the closest of a continuous series of supermoons that recur monthly, each varying in degree. Comets are wild cards, unpredictable visitors that occasionally rival or even surpass the moon in brightness, but do so rarely and without reliable schedules. This comparison highlights two very different types of cosmic phenomena: the predictable cyclic motions of bodies locked in regular orbits versus the chaotic, punctuated appearances of comets emerging from the outer darkness. Part 14. 2060, the brightest comet ever. In 2060, something extraordinary will occur, an event no living human has ever witnessed. The forecasts are finalized, the orbital calculations complete, and astronomers are marking their calendars for a spectacle that will rival anything in recorded history. A massive object from the Oort cloud, that distant reservoir of comets surrounding our solar system, is hurtling toward the inner solar system on a trajectory that will bring it close enough to the sun to become truly spectacular. Not just bright, not merely visible, but potentially as luminous as the moon itself, dominating the night sky for weeks, perhaps even months. If the predictions hold true, this comet will be the astronomical event of the century, a once-in-a-lifetime spectacle, visible even in daylight, casting shadows at night, and fundamentally transforming humanity's relationship with the sky for everyone lucky enough to witness it. Let me put this into perspective. Most comets that pass through the inner solar system are faint, requiring binoculars or telescopes to spot. Only a handful each decade become visible to the naked eye, appearing as fuzzy patches of light with modest tails. Every few decades, a bright comet arrives, one that makes headlines and draws people outside to gaze upward. Comet Hale-Bopp in 1997 was one of these rare visitors, visible for over 18 months, and bright enough to be seen easily even from cities plagued by light pollution. Before that, Comet West in 1976 put on a spectacular show for those who woke before dawn to catch a glimpse. And of course, there's Halley's Comet, which returns every 75 to 76 years and has been documented by humans for over 2,000 years, appearing in Babylonian records, Chinese chronicles, and the Bayeux Tapestry. But even Halley's Comet at its brightest is still just a bright comet. It's impressive, certainly, but it doesn't dominate the sky. The 2060 comet, if it lives up to its billing, will do exactly that. Current models suggest it could reach an apparent magnitude of 10 or even 12, making it as bright as a half moon, or possibly even a full moon. To grasp what this means, remember that the magnitude scale is logarithmic and inverted. The lower the number, the brighter the object. For comparison, the Sun's apparent magnitude is 26.7. The full moon shines at about 12.7. Venus at its brightest reaches around 4.9. A bright comet like Hale-Bopp peaked near magnitude 0. Each step on the magnitude scale represents roughly 2.5 times more light. So a magnitude 10 comet isn't just twice as bright as Hale-Bopp, it's thousands of times brighter. What creates a comet this spectacular size matters. Obviously, the nucleus of the 2060 comet is estimated to be absolutely enormous, possibly 50 to 100 kilometers across, making it one of the largest objects ever to visit the inner solar system from the Oort cloud. For comparison, the nucleus of Comet Hale-Bopp was roughly 60 kilometers across, and that was already considered huge. But size alone isn't enough. The comet also needs to pass close to the Sun, close enough that solar heating vaporizes massive amounts of ice, creating a coma that can grow larger than Jupiter, and a tail stretching for hundreds of millions of kilometers. The 2060 comet checks all these boxes. Its perihelion will bring it within about 0.3 astronomical units, roughly 45 million kilometers, well inside Mercury's orbit. At that distance, the Sun's heat will vaporize not only water ice, but also more volatile compounds like carbon monoxide and carbon dioxide. Yet beyond the science, something deeper is unfolding. For one brief moment in 2060, humanity will share a common experience. People in every country, on every continent, will look up and see the same spectacular sight. A comet so bright, it can't be ignored. So spectacular, it transcends language, culture, and politics. The 2060 comet will be impossible to miss. It will dominate the twilight and nighttime sky, visible even from brightly lit cities, casting enough light to read by if you're in a dark location. And here's where things get interesting, maybe even a little unsettling. What happens when you introduce a light source into the night sky that rivals the moon? We already know that moonlight influences ecosystems. Nocturnal animals adjust their behavior with lunar phases, and predators hunt differently during full moons. Human circadian rhythms, the internal clocks regulating our sleep-wake cycles, are also shaped by ambient light levels. For the entire span of human existence, the moon has been the brightest object in the night sky. What happens when we throw a third variable into that equation? The truth is, we don't know. The comet will be visible for weeks, possibly months, and during that time it will flood the nighttime environment with light at levels Earth hasn't experienced from a comet in recorded history. Now let's talk about the less pleasant possibilities. Whenever a comet gets this close to Earth, concerns about impacts and catastrophes inevitably arise. Let me be clear, the 2060 comet is not going to hit Earth. Its orbit is well characterized and it will miss us by millions of kilometers. But that doesn't mean it's completely harmless. Comets shed material as they approach the Sun. Dust, small particles, and sometimes even larger fragments break off and spread out along the comet's orbit. If Earth's orbit intersects this debris stream after the comet has passed, we could experience a spectacular meteor shower. But there's a more concerning scenario, one that, while unlikely, isn't impossible. Comets sometimes break apart as they approach the Sun. Thermal stress, tidal forces, and outgassing pressure can all cause structural failure in a comet's nucleus. If the 2060 comet were to fragment, and if one of those fragments happened to have an orbit bringing it closer to Earth, than predicted, we'd have a serious problem. The odds are extremely low, but it's not impossible. This is why asteroid and comet tracking has become such a serious endeavor. But hopefully, the dominant response will be awe, because whatever else it is, the 2060 comet will be beautiful. It will remind us that we live in a universe capable of creating truly spectacular phenomena. For weeks or even months, dinner conversations will revolve around tail structures and coma dynamics. Children will stay up late to catch a glimpse of the comet. It will become woven into the cultural fabric of that generation. And when it's over, when the comet has swung around the sun and is heading back to the outer solar system, we'll be left with photographs and memories. But even as it fades, another date on the cosmic calendar awaits an equally profound milestone. Part 15, 2177, Pluto's first birthday and cosmic reflection. On February 18, 1930, a young astronomer named Clyde Tombaugh was examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was searching for a predicted ninth planet, a world beyond Neptune, that might explain slight irregularities in the outer planet's orbits. The work was tedious, comparing pairs of photographs taken days apart, searching for anything that moved against the background of stars. And then he found it, a tiny dot that had shifted position between exposures. Planet X, the ninth planet, Pluto. The discovery made headlines worldwide. Pluto was the first planet discovered by an American, capturing the public imagination in a way few astronomical discoveries ever do. The name Pluto, suggested by an 11-year-old girl in England named Venetia Burney, seemed perfect, the god of the underworld, for the distant dark world at the edge of the solar system. For 76 years, schoolchildren were taught that the solar system had 9 planets. Pluto, small and mysterious, was the final outpost before the vast darkness of interstellar space. Then, in 2006, the International Astronomical Union redefined what it means to be a planet. Pluto met 2 of the 3 criteria, but failed the third. It hadn't cleared its orbital neighborhood of other debris. Under the new definition, Pluto was reclassified as a dwarf planet, returning the solar system to 8 planets. The demotion sparked surprising public outcry. People had grown fond of Pluto, this distant underdog world. But here's something that puts it all into perspective. In 2177, 247 years after its discovery, Pluto will complete exactly 1 full orbit around the Sun. It will return to the exact same spot in space where Clyde Tombaugh first observed it on those photographic plates. Let that sink in. Pluto's year, what it takes to complete a single orbit, spans 247.9 Earth years. When Pluto was discovered in 1930, it had already completed just about 36% of its orbit since the Declaration of Independence was signed. We discovered Pluto, studied it, sent a spacecraft to fly by it in 2015, watched it get demoted, and debated its status endlessly. And through all of this, Pluto hasn't even completed a single orbit around the Sun. This serves as a profound lesson in the vastness of time. As humans, we live at best about 80 to 100 years, our lifetimes confined to a brief span of direct memory and experience. In contrast, our civilizations stretch back much longer, with continuous written records extending about 5,000 years. Even on such a grand scale, Pluto has completed only around 20 orbits. In the context of human civilization, this means we've only witnessed 20 trips around the Sun for this distant world. When we expand our view to the 4.5 billion year history of the solar system, Pluto has made roughly 18 million orbits. That may sound like a huge number, but it's just a drop in the cosmic ocean, until you fully grasp the mind-boggling fact that Earth has completed 4.5 billion orbits in the same span. But it's not just Pluto. The outer reaches of our solar system are governed by timescales that completely dwarf human perception. Neptune, for instance, takes a staggering 165 years to complete just one orbit around the Sun. Since its discovery in 1846, Neptune has barely managed to complete even a single orbit. Uranus takes 84 years. Saturn takes 29. These are worlds that glide through the zodiac with a slow, deliberate pace almost imperceptible to the naked eye. Ancient astrologers were only aware of 5 planets beyond Earth because in their time, those were the only ones that moved visibly across the sky within the span of a human lifetime. And this brings forth a fascinating question. What is the greatest stretch of time that the human mind can genuinely grasp? We intellectually acknowledge that the universe has existed for 13.8 billion years, that the Sun ignited its fiery core 4.5 billion years ago. We can recall these immense figures, embed them in textbooks, and pass them on to eager students. But do we truly grasp these vast spans? Can any human mind genuinely hold 13 billion years in a way that feels tangible, real? Most likely not. Our intuition is wired to the rhythms of human lifetimes, the years we expect to live. Beyond a handful of generations, time slips into abstraction. That's why Pluto's first birthday since its discovery resonates so deeply. It marks a timescale that's just barely within the reach of our civilization's comprehension. A span of 247 years, from 1777 to 2177, stretches well beyond any single human lifetime, far surpassing the lifespan of most institutions, yet remains short enough for us to trace a thread of cultural continuity. People living in 2177 will still be able to look back at the records of Pluto's discovery and truly understand what those astronomers were doing and why it mattered. But when Pluto completes that first orbit in 2177, it will only be starting its second orbit since discovery, and that second orbit will stretch another 247 years. Pluto won't finish its third orbit until 2671. The people who witness Pluto's second birthday haven't even been born yet and won't arrive for centuries. By then, will humans still care about Pluto? Will we still be gazing at the skies, tracking the planets, marking these cosmic milestones? I'd like to believe we will. Despite everything, despite the chaos that so often defines human behavior, we've maintained astronomical observatories for centuries. We've preserved records, handed down knowledge, and built upon the discoveries of those who came before us. The very fact that we can calculate Pluto's orbit and predict its position in 2177 stands as a powerful testament to the collective strength of human knowledge forged by generations working together toward shared goals. And speaking of vast stretches of time, consider this: when 3I Atlas entered our solar system in 2024, it had been drifting through interstellar space for millions of years. If it was ejected from a star system 10 light-years away, traveling at 66 km/h, it would have taken roughly 45,000 years to make that journey. Throughout all that time, this comet remained frozen, unchanged, silently gliding through the endless void. And then, after just a few months in our solar system, it was destroyed by the Sun, vanished without a trace. Yet understanding is not the same as experiencing. We can calculate Pluto's orbit, but we can never truly feel what it's like to take 247 years to complete one circle around the Sun. We can measure the Sun's lifetime at 10 billion years, but we can't viscerally grasp the weight of that immense span. We're bound by our biology, our mortality, our place in space and time. When Clyde Tombaugh discovered Pluto in 1930, he was just 24 years old. He passed away in 1997 at age 90, having witnessed spacecraft visit every planet in the solar system and humans walk on the moon. But he never saw Pluto complete a full orbit. No human alive at the time of Pluto's discovery will live to see its first birthday. That milestone will belong to people not yet born.